Night gathers without hurry. Stars lean into distance, their bright syllables fading, and a deeper consonant moves beneath them, a quiet gravity that does not shout. Somewhere beyond visible comfort, a region forms where light no longer negotiates with space, where the path forward narrows into a patient curve. The mind names it a black hole, then listens. In that listening, the sky seems to breathe. The vast structure does not chase, does not rage, does not reach out with flames. It simply waits, a bowl carved into the fabric of the cosmos, unruffled by the winds that push galaxies around. Anxiety arrives, then ebbs, because this presence refuses drama. It is a still lake in the mountains of space-time, and even photons, skimming like water striders, eventually find the surface too smooth to escape. The story begins with a feeling rather than a sight. No glowing colors mark the boundary, no thunder announces the threshold. A black hole is an absence framed by law, a place where geometry grows deep enough to cradle motion. The stars around it whirl in elegant obedience, their arcs bending into soft bracelets of light. Every orbit is a lullaby counted in years and centuries, a metronome slow enough to steady thought. While matter elsewhere chatters in explosions and bursts, here the conversation is paired to essentials. Mass speaks to curvature, curvature speaks to motion, motion quiets into alignment. The result is silence that feels earned. Time behaves differently in this quiet. Clocks nearer the gravity well tread carefully, their seconds stretched like silk. A distant observer would swear that everything near the edge moves in syrup, that brightness dims, not from reluctance but from the calm patience of redshift. The universe teaches restraint in this neighborhood. Rush, and the path twists tighter. Linger, and even lingering becomes an act of devotion to the rules written into space. The equations that define the horizon read like a soft mantra, simple symbols balanced with care, guiding the mind towards stillness rather than surprise. A black hole's boundary is not a wall. It is a one-way shore where the river flows only inward. To approach it is to notice how scenery slows, how trajectories straighten into inevitability. Nothing is forced from outside. The curvature merely offers a more and more persuasive suggestion. A pebble near a valley slides not because the hill rages, but because the valley exists. So too with this cosmic basin, light itself accepts the counsel. Paths that once ran free begin to arc, then spiral, then vanish beneath a line that has no texture and no sound. That vanishing does not feel like erasure. It feels like completion, as if motion found its final chord and allowed it to ring. The mind imagines the center as fury, yet the truer picture is clarity. There is almost nothing performative here. Rotation, if present, is described by a clean parameter. Mass is summed with exquisite simplicity. Even electric charge, rare in astrophysical practice, folds into the minimal ledger. The complex histories of collapsing stars are smoothed into an uncomplicated present. Standing back, a viewer might understand the impulse to call such an object bald, stripped of ornament. But that spareness is not severe. It is restful. It removes the noisy signatures of origin and leaves only the gentle arithmetic that anchors the surrounding sky. Around some of these objects, matter gathers and warms. From a distance, that glow becomes a lantern hung over a door that will never open outward again. The lantern flickers, swirls, and occasionally sends out a straight line through the dark, but the door behind it remains perfectly still. The contrast comforts. Activity can dance nearby, and yet the central character keeps its poise. Turbulence loses authority in the face of such composure. The message is not that the universe is free of storms, but that storms can be observed from a vantage where the heart does not have to accelerate. Listening continues, and a subtler texture appears. Gravity hums at a pitch too low for ears, yet instruments have taught that ripples can travel and that space-time itself can carry a wave. Imagine distant pairs meeting, circling, closing, and at their final embrace sending a deep tone across the void. That tone passes through matter and mind with little friction. It resembles the steady rocking of a boat in a protected harbour. The cosmos, usually shy about revealing its structure, here allows the fabric to sing. The song is not frantic. It is measured, regular, and persuasive enough to slow breathing in sympathy. Fear, so often tied to the unseen, softens in the presence of order. The black hole is hidden, yet its effects are traceable, its outlines inferred with care. The discipline of calculation turns the unknown into a trusted silhouette. Even quantum hints, faint and tentative at the rim, feel like the gentle heat of a sleeping ember rather than a conflagration. Darkness is never fully absolute. There is always some small negotiation between the edge and the emptiness beyond it, an exchange so slight it might be mistaken for a sigh. Scale helps the mind rest. These objects can be small by cosmic standards or so large that the orbits of whole star systems would fit comfortably within their quieter regions. In either case, their presence simplifies the neighborhood. Stars find lanes, gas finds choreography, and galaxies find a center of gravity that steadies their luminous arms. The night becomes an architecture rather than a wilderness. The eye gazing outward feels less like a lost wanderer and more like a respectful visitor to a cathedral where ceremony never ends and no voice rises above a whisper. There is a temptation to treat this calm as a mask for violence, yet the mask metaphor fails. Masks conceal. This calm reveals the rules. Gravity is not a tyrant here, it is a patient teacher. Energy, momentum, and curvature exchange notes with the politeness of musicians tuning before a long performance. Any drama that once accompanied the birth of such an object has long ago dissolved into equilibrium. What remains is cadence. What remains is form. That form is not rigid. It is supple. It welcomes orbits. It shapes the tides of light. It permits warm disks to settle and cool. And it accepts every traveler who crosses the shore without judgment or haste. Meditation in the cosmic sense means recognizing what cannot be hurried. The geometry around a black hole cannot be talked into surrendering its secrets all at once. It requests attention over long periods, offers evidence in graceful arcs and delayed echoes, and rewards patience with pictures that are more suggestion than portrait. That restraint invites comfort. The mind that encounters it can let go of quick answers and allow the body to remember slow rhythms. Astronomy becomes a form of breathing. Numbers become a lull. Even language calms in this domain. Words grow shorter. Mass, spin, edge, light, fall, curve. The cadence of these syllables mirrors the simplicity of the object itself. There is no need for intricate adjectives when the nouns already place the listener at the threshold of wonder. The silence between terms does much of the work, the way the gap between stars does most of the shining. In this sparse vocabulary, imagination finds room to stretch and rest at the same time. All of it gathers into a single feeling, a steadying trust in the deep structure of things. The black hole is not a monster lurking in midnight. It is a proof that the universe contains spaces where the rules hold with a grace that soothes. Light enters, light does not return, and from that fact arises not dread, but a gentle acceptance that some doors are meant to close. The night, faced with such certainty, relaxes. Hearts that measure themselves against it find a slower beat. In that rhythm, sleep approaches, not as escape, but as alignment with the most patient curve ever drawn. In an English rectory during the 18th century, a clergyman who loved lenses and gravity wondered how bright a star could be before light itself failed to depart. John Mitchell set the thought on paper with quiet confidence. If a star grew compact enough, he reasoned using Newton's escape speed, even light would not outrun the pull. He called the result a dark star, not a terror, simply an implication of an equation. The idea drifted through letters and journals like a shy visitor at a learned gathering. Pierre-Simon Laplace repeated the argument later, placing the notion inside a neat paragraph as if shelving a careful instrument. No boundary layers, no quantum hints, only classical gravity and the fastest speed anyone could imagine. It was a shadow cast by mathematics across a sky, not yet prepared to see it. Centuries shift their furniture slowly. Telescopes lengthen, prisms split brightness into patience, and physics relights its foundations. In the early 20th century, space and time stop behaving like separate rooms. Albert Einstein composes a geometry where mass tells space-time how to curve and curvature tells mass how to move. The equations arrive like a new map for a landscape that had always been there. War and illness swirl around the world. Yet, in a hospital bed in 1916, Karl Schwarzschild solves Einstein's field equations for a perfectly spherical mass. The solution is exact, unadorned, and astonishing. It says that for a certain radius, a surface forms beyond which paths all tilt inward. The math does not flinch, even if intuition hesitates. The term event horizon has not yet settled into language, but the feature exists, as inevitable as the surface of a lake. Schwarzschild's radius is compact, smaller than any ordinary star can be, without collapsing. The geometry suggests a one-way shore, not as an invention of imagination, but as the logical consequence of the new theory's grammar. There is no need to invoke friction, viscosity, or any tangible mechanism. Space-time itself provides the structure. The solution carries a coordinate singularity at the horizon, a mathematical wrinkle that later mines smooth by changing charts. At the center, a different singularity resists such smoothing, a point where curvature soars and classical description runs out of breath. For a time, many treat these results as curiosities. Stars, after all, are thought to be upheld by pressure and fusion. The cosmos is wide, the actors numerous, but the stage is assumed to be gentle enough to avoid extremes. Then observations of stellar deaths sharpen. White dwarfs carve a limit into theory. Neutron stars appear in equations as compressed remnants. The old suspicion returns with new muscle. Perhaps nature does not stop at merely dents. Perhaps some stars end by sinking entirely through their own geometry until only a horizon remains. In 1939, J. Robert Oppenheimer and Hartland Snyder write down a model of gravitational collapse. They show that an idealized sphere of dust, if massive enough, will contract past any pressure rescue and hide behind a boundary from which no signal can return. To a distant witness, the surface appears to slow and fade, approach without arriving. To matter riding the collapse, crossing occurs in finite time, with no dramatic alarm at the threshold. The two views are not contradictions. They are coordinate perspectives, each allowed by relativity's patient rules. The paper is spare. It reads more like a demonstration than a proclamation, yet it moves the conversation from maybe to must. Language catches up. In the mid-20th century, as radio dishes listen and X-ray detectors climb into orbit, evidence grows that compact objects feed on nearby gas and shine by heat alone. The term black hole, popularized by John Wheeler, forms in lecture halls and finds a home in print. The name is simple, tactile, and precise. It names not a substance but a region defined by paths light cannot follow outward. Meanwhile, Roger Penrose proves that, once a trapped surface forms, a singularity is unavoidable under broad conditions. The conclusion does not depend on symmetry or nicety. It depends on the structure of causality and the focusing power of gravity. The theorem replaces hunch with certainty about the inward destiny of collapse. The mind, standing in this lineage, hears an unexpected soothing. These ideas do not emerge from spectacle. They drift quietly from patient reasoning, from questions posed at a desk, from symbols balanced on a chalkboard until they stop wobbling. Early speculations about dark stars fold into the exactness of space-time curvature. Heuristics become theorems. Skeptical pauses become working assumptions. The arc is not a chase through crisis, but a gentle deepening of an answer already outlined by gravity's oldest instincts. Once mass and distance pass certain thresholds, the path bends inward without regret. Astronomers begin to search for footprints that match the theory's steps. Stars in binary systems wobble as if pulled by heavy partners that refuse to shine. Gas near invisible companions heats to X-ray temperatures. At the centers of galaxies, stars move like dancers, obeying an invisible choreographer, their speeds implying a mass compact enough to fit within the delicate ellipse of a planetary system. None of this requires drama. The case strengthens through accumulation. Each measurement adds a stitch to a quilt whose pattern was predicted by equations written in silence years before. The language of parameters simplifies the personality of these objects. Mass sets the scale. Spin imprints a gentle twist, frame dragging that pulls nearby paths into a slow swirl. Charge rarely matters on cosmic scales and is usually negligible, leaving a two-number whisper to describe an object that can outweigh millions of suns. The elegance is not austere, it is comforting. A complicated birth story ends in a stately form that does not clutter the sky with unnecessary details. Identity collapses into a minimal catalogue, and from that catalogue flows a full set of behaviors the universe can rely upon. Photons circling at the photon sphere draw a ring that later cameras will trace. Inside that orbit, nothing bounces back. Outside, light still curves and carries news to distant eyes. The horizon does not glow, does not resist, does not speak. It records by area and waits by geometry. That quietness encourages instruments to calm as well. Interferometers align their arms. Radio dishes combine into one global ear. The observational effort mirrors the object's personality. Patient, coherent, unhurried. Each team chooses integration, time over impulse, signal stacking over spectacle. Quantum fields will enter the conversation and add a faint warmth later. For now, the path from Mitchell's dark star to modern horizons stands on pillars that do not demand esoteric vocabulary to remain upright. Escape speed gives way to null geodesics. Newton's force yields to curvature. The difference is not cosmetic, it is foundational. Yet the mood remains the same calm insistence that the universe follows simple lines when conditions allow. When mass compacts enough, a boundary forms. When the boundary forms, outward light no longer exists for that region. The cosmos, normally extravagant, becomes economical. This history offers a tranquil lesson about discovery itself. New ideas do not always crash through doors. Sometimes they arrive as quiet consequences of the laws already trusted. A star that cannot let light go was once a sketch in a footnote. Then it became an exact solution, a theorem, an observation, and finally a picture that would echo around the world. Each step replaced noise with clarity. Each step invited the mind to relax into confidence that the sky is legible when looked at long enough. The narrative does not require urgency. It asks only for attention. By the time the modern era settles in, the term black hole carries no menace among those who study it daily. It represents a stable endpoint for certain masses, a dependable feature in galactic neighborhoods, and a laboratory for understanding gravity at its purest. The fear once attached to the unseen dissolves into routine. Equations predict, observations confirm, and the cosmos continues its measured pace. The first whispers of darkness have become a calm voice that explains its own existence without raising its volume. Einstein's equations rest like carved stone beneath the shifting weather of theory. They describe a universe where mass and energy bend the very stage upon which all motion plays. In their curves, the concept of force gives way to geometry. The notion of falling becomes nothing more than moving straight through a curved space. It is a serene replacement for the old Newtonian tug, less about pull and more about the shape of possibility. Among all the solutions that the equations allow, the one describing a black hole glows quietly with finality. It does not contradict intuition, it extends it. The equations do not need violence to explain collapse. They need only the grace of curvature deep enough to close upon itself. Relativity's transformation is not loud. It feels more like a slow inhalation of understanding. Where once gravity was a command shouted across the void, now it is the gentle persuasion of space-time guiding everything toward balance. In this framework, even chaos seems choreographed. Orbits spiral, but they do so according to an invisible rhythm, a rhythm written into the structure of the metric itself. To enter a strong gravitational field is not to be captured by cruelty, but to participate in the most patient architecture the cosmos knows. In this curvature, light plays the role of both messenger and prisoner. Rays that once stretched confidently through open space now trace arcs around invisible wells. To a far observer, these paths reveal the existence of something profoundly calm, a region where geometry grows deep enough to silence escape. At the mathematical surface defining that silence, space-time folds inward perfectly. The effect is not cataclysmic, it is elegant. Like water filling a bowl, the continuum settles into its most stable form. The event horizon, far from a wound in the universe, is its smoothest contour. What began as Einstein's abstraction quickly became the cradle for a new image of reality. A black hole's horizon can be thought of as the ultimate equilibrium surface. Nothing disturbs it, nothing escapes it, and nothing faster than light can outpace its invitation. In that stillness lies an astonishing coherence. The equations insist that the horizon is not chaos but symmetry. Every possible motion aligns precisely with the inward tilt of spacetime. There is no friction, no protest, only continuity. The universe itself has found a state of rest so complete that even time surrenders to it. Einstein himself doubted the physical existence of such regions. To him, they were artifacts, mathematical curiosities born of simplifying assumptions. Yet the logic refused to fade. Others took up the challenge, exploring the idea that perhaps nature was not merely capable of such perfection, but eager to demonstrate it. Over time, the theoretical horizon began to appear less like a mathematical toy and more like an inevitable conclusion. Relativity, in its unhurried exactness, leaves no room for exceptions when enough mass compacts within a small enough space. The curvature closes, and space-time turns its interior gaze upon itself. There is serenity in this inevitability. The laws of general relativity do not strain to produce a black hole. They simply allow the universe to do what it already tends towards: simplicity. Energy condenses, symmetry deepens, equations shorten. Every step toward greater density is a step toward fewer moving parts. It is a mathematical meditation, the cosmos relaxing into minimal form. The equations describe this without hesitation, mapping the journey from scattered particles to perfect curvature as though following a lullaby composed by gravity itself. Near the horizon, time behaves with unassuming strangeness. To an observer far away, an infalling clock appears to slow, its hands drifting towards stillness, its light reddening into invisibility. Yet for the clock itself, the passage remains ordinary. It crosses the horizon without shock, continuing its descent unaware of the silent transformation witnessed from afar. This duality of motion that is both eternal and immediate adds to the calm paradox of relativity. The same event can be frozen and flowing at once, depending only on where one watches. Time itself becomes flexible, not broken but patient. To understand this, physicists rely on the metric tensor, a mathematical object that records how distances and durations behave in curved space. In the presence of a massive body, its components shift delicately, altering the geometry in precise, predictable ways. Near a black hole, the metrics terms whisper an extraordinary truth. Space and time trade roles. The inward direction behaves like time, always advancing. Outward movement becomes as restricted as travel into the past. Yet the transition is smooth. There is no boundary carved by force, only the natural consequence of a geometry folding into itself. This curvature acts like a soft cushion for the laws of motion. Objects do not crash against an invisible wall, they simply follow geodesics, the straightest paths available in curved spacetime. Falling, then, is nothing more than obeying the natural line drawn by geometry. It is surrender, not conflict. Every planet, every photon, every drifting atom near a black hole becomes part of an immense choreography conducted in silence. The effect is tranquil because it is absolute. No deviations, no friction, no noisy. Mathematically, the Schwarzschild and Kerr solutions describe these conditions with a grace that borders on art. In them, curvature and rotation intertwine with impeccable economy. There are no extraneous parameters, no untidy leftovers. Einstein's field equations, complex in their derivation, yield outcomes that feel inevitable once written. A black hole, viewed through this lens, is not an aberration but the simplest possible conclusion to gravity's narrative. It is what happens when the universe stops resisting its own logic. The mind contemplating these results can rest. There is no need for metaphors of devouring monsters or cosmic doom. What general relativity describes is balance mass in dialogue with space, space responding with curvature, curvature guiding motion toward harmony. This is the serenity hidden within Einstein's mathematics. A picture of gravity not as a threat, but as a sculptor, shaping the cosmos into elegant forms that hold even light in gentle persuasion. The recognition of this calm order changed the emotional language of physics. It replaced fear with comprehension. It gave astronomers a reason to look at the night sky and see not random violence but sustained design. The curvature that defines a black hole's horizon is also the curvature that keeps planets steady, galaxies coherent, and cosmic expansion smooth. It is the same principle, simply taken to its most refined state. In that realization, the universe feels less like a battlefield of forces and more like a vast poem written in differential geometry. Thus, Einstein's curve becomes a cradle. The theory that once described the bending of starlight during an eclipse extends its arms to encompass the deepest gravitational wells. The mathematics that guide the gentle fall of a planet also describe the quiet absorption of light itself. The same fabric stretches across every scale, from orbit to horizon, from motion to stillness. In this continuity lies reassurance. The cosmos is consistent, the night is lawful. Gravity is not chaos, but grace folded into form. The edge of a black hole is not an edge at all, but a gradient, an invisible slope, where geometry changes from ordinary to irreversible. It is known as the event horizon, though it is not an event, and not a horizon in any terrestrial sense. There are no cliffs, no sparks, no sound. Only the calm certainty that once light crosses that invisible surface, it will never return. The silence that defines this region is absolute, yet not cold. It is the silence of completion, of a process that has reached its final, simplest form. To approach the horizon in imagination is to experience the slowing of the universe itself. A traveler descending toward that line would see the stars above blue shift into brilliance, then red shift into dimness, until the cosmos fades into an infinite stillness. Time stretches, obedient to gravity's quiet hand. To the distant observer, the traveler never quite arrives. They seem to pause forever just before the threshold. But the traveler feels no pause, only the smooth continuation of fall, the acceptance of inevitability, no crash, no fire, just a surrender to the curve of space-time. This paradox of perception is one of relativity's most delicate gifts. The horizon becomes a mirror for how perspective sculpts reality. Each vantage holds its truth, neither falsifying the other. To the outside world, the surface of the black hole is a place where time itself stops. To the infalling object, it is simply another moment on an endless path. The equations confirm both. In that duality lies the strange comfort of general relativity. Truth does not demand singularity of view. It allows coexistence of multiple quiet certainties. Around this silent region, light performs its last dances. Some photons skim the surface at precise orbits, forming what physicists call the photon sphere, a circular track where radiation moves forever sideways, caught between escape and return. Any small disturbance sends them spiraling inward or outward, but while they last, their orbit forms the innermost shimmer of the black hole's halo. It is from these trajectories that the shadow's outline is born, the dark center surrounded by a ring of light curved by gravity's gentle persuasion. Beyond the photon sphere lies the accretion disk, the luminous veil that makes black holes visible to human instruments. Here, gas drawn from nearby stars spirals inward, heating through friction until it glows in X-rays. The light it emits is chaotic, yet its motion obeys elegant order. Every particle, every swirl of plasma, traces the invisible architecture set by Einstein's equations. What seems violent is mathematically precise. The dance of infalling matter becomes a cosmic ballet, choreographed by curvature. And at the center of this brightness, the source of all this motion remains the stillness of the horizon, perfectly silent, perfectly unchanging. To those who study it, the event horizon's simplicity is its greatest mystery. Nothing that crosses it can ever return to report what lies within. All the information about what fell inside is erased from the outside view, replaced by just three quiet parameters: mass, spin, and electric charge. This economy of description is astonishing. A star with complex chemistry, turbulent layers, magnetic storms, and radiation fields collapses into an object describable by three numbers. The black hole forgets its origin completely, preserving only what the universe must keep: those traits that define the geometry of space itself. Everything else dissolves into anonymity. The calmness of this loss holds a strange appeal. Human minds, often burdened by detail and memory, find in the horizon's amnesia an echo of peace. Nothing is wasted, but nothing is carried. The black hole continues, indifferent yet balanced, its surface expanding slightly with every new arrival, its gravity deepening in perfect proportion. The mathematics ensure conservation. The serenity comes from that assurance. Nothing is arbitrary here. Every disappearance is matched by exact adjustment, as if the universe maintains quiet bookkeeping at the border of eternity. Inside the horizon, theory suggests a region of increasing curvature, a descent toward what equations call a singularity. Yet even that term misleads. It does not denote a thing, but a limit beyond which the current language of physics cannot speak. What lies there is neither destruction nor creation, but silence in its purest mathematical form, the end of describable geometry. The mind recoils from that blankness, but it is a clean blankness, not a fearful one. It marks the edge of comprehension, not of existence. The event horizon itself does not resist inspection. It obeys rules with exquisite precision. Its area can never decrease, a law discovered by Stephen Hawking, suggesting that the boundary of no return grows only when new mass or energy joins it. This gives the horizon a quiet directionality, a time-like arrow embedded in its very shape. Though the process cannot be reversed, it does not imply loss in the emotional sense. Instead, it speaks of progression, of nature's tendency to settle into ever more stable configurations. Entropy, that universal accountant, finds its calmest expression here. Physicists have learned to read the horizon through light that never touches it. By observing how radiation bends and delays near its rim, they extract clues about its size and rotation. The data arrive as numbers, but what they reveal is a portrait of serenity, an object so perfectly defined that its description contains no remainder. Observatories across the Earth, linked in synchronization, have captured these signatures, tracing in radio waves the faint ring that outlines absence itself. What they found was not chaos, but order of astonishing clarity. For the cosmos, such stillness is not rare, it is fundamental. Every star, every orbit, every whisper of radiation obeys the same field equations that sculpt the event horizon. The black hole is simply where those equations express themselves most purely. Its calm is the distilled essence of universal law. No flicker of quantum uncertainty or galactic collision can disturb its geometry in any measurable way. Time near it slows into an endless sigh. Space bends into a perfect cradle. The edge where sound, sight, and signal end is not an end to thought. It is an invitation to reflection. In the quiet of that mathematical boundary, one feels the weight of cosmic patience. Billions of years pass in the outside universe while, for an observer falling in, mere seconds elapse. The horizon does not protest this difference. It simply exists at the intersection of two truths. In doing so, it teaches that tranquility is not the absence of motion, but the coexistence of perspectives that no longer argue. The event horizon, once thought to be the ultimate limit, becomes instead a symbol of peace through inevitability. Everything that approaches it becomes part of a larger continuity, absorbed not in violence but in perfect conformity to law. The universe, through the geometry of a black hole, demonstrates that even endings can be graceful. There is no spectacle here, no cry, no flame, only the steady quiet at the edge where light rests. At first glance, the physics of a black hole seems complete. Its mass, spin, and charge are all that matter. Yet the more carefully scientists study these dark regions, the less certain simplicity appears. Observations sharpen, and what once seemed absolute begins to shimmer with unanswered questions. The horizon that appeared perfect now hides subtler textures. Quantum theory, ever restless, steps into relativity's calm domain and begins to whisper. Space-time, even at its most graceful, may still tremble with secrets. The mystery deepens when the universe's two great languages, quantum mechanics and general relativity, try to speak to each other near a black hole. Relativity describes smooth curvature, continuous, and serene. Quantum mechanics speaks in the staccato grammar of probability, of particles flickering in and out of existence. When applied to the same place, their stories do not quite agree. At the event horizon, this disagreement is not a shout, but a murmur of contradiction. The equations, so harmonious separately, begin to hum out of tune together. In 1970, this quiet discord became visible through thought experiments. If quantum fields hover near a black hole, The vacuum itself changes character. Pairs of virtual particles continually appear and annihilate, borrowing energy from nothing for a heartbeat before returning it. But at a horizon, one of each pair may fall inward while the other escapes. To distant observers, the escaping particles look like radiation, a gentle exhalation of energy from the black hole's edge. It is a slow leak, almost imperceptible, yet it implies something extraordinary. Black holes are not perfectly black. Stephen Hawking's calculations revealed this with surprising calm. The temperature of this radiation is inversely proportional to the black hole's mass. The larger the hole, the colder it is. A supermassive one at a galactic center glows only in theory, too faint to detect. A small one would evaporate faster, shining briefly before fading. This discovery did not scream against prior physics, it whispered it into a new shape. What had seemed eternal now had a life cycle. Even the most stable darkness in the universe was subject to time's eventual erasure. This insight should have settled comfortably into theory, but it introduced another layer of unease. If black holes radiate, then over unimaginable epochs they can evaporate completely. What, then, becomes of the information about everything that once fell in? Quantum mechanics insists that information cannot be destroyed. Relativity seems to allow it. Between these two doctrines hangs a paradox as gentle as it is relentless. The more physicists try to reconcile them, the more intricate their dialogue becomes. The growing tension between the quantum and the geometric turns the black hole from an endpoint into a question mark. The event horizon, once the final word in gravitational calm, becomes a stage for subtle debates. Does information escape, encoded somehow in the radiation? Or does it remain hidden, preserved within a universe folded inside the horizon? Each theory offers comfort only until examined closely, at which point its seams show. The black hole, in its stillness, provokes the deepest restlessness in modern physics. Meanwhile, observation continues to surprise. Jets of matter blast from the poles of active galactic nuclei, streams of plasma moving nearly at light speed, launched by mechanisms not yet fully understood. The black hole itself emits nothing, yet its surrounding environment becomes one of the brightest phenomena in the universe. This contradiction, light emerging from darkness, adds another twist to the story. Gravity, though inescapable, enables creation as much as confinement. What should have been an ending becomes a source. At cosmic scales, entire galaxies organize themselves around these central masses. Their quiet pull sculpt structure out of chaos, guiding star formation, dictating rhythm, setting tempo. Yet as astronomers map these patterns, they find variations too nuanced to fit cleanly into theory. Some galaxies house surprisingly massive black holes for their age. Others shelter small ones, despite abundant matter. The balance between growth and restraint is precise, but not yet fully explained. The dark hearts at galactic centers remain steady, but their history refuses simplicity. Mathematicians probing the equations find similar complexities. Solutions that once looked perfect begin to branch into exotic forms. Rotating black holes with ergospheres where space-time itself is dragged along. Hypothetical charged black holes whose electric fields warp geometry into strange, layered spaces, and even speculative wormholes connecting distant regions. Each variation complicates the tranquil image painted by Schwarzschild's original work. Each reveals a deeper, richer structure, hiding behind the apparent uniformity of mass and spin. As instruments improve, the evidence of these subtleties grows. The Event Horizon Telescope's images show not a flat darkness, but a textured ring shaped by magnetism and motion. X-ray spectra reveal hotspots orbiting so close to the horizon that relativistic beaming stretches their light into trembling arcs. Simulations capture turbulence like ocean waves breaking against an invisible shore. Yet the black hole remains stoic, its essential calm undisturbed. Complexity dances at its edge, while its core refuses movement. For the human mind, this contrast is magnetic. It suggests that serenity does not require simplicity, that stillness can contain infinite intricacy without losing composure. A black hole embodies that paradox more completely than any other known object. It is both final and evolving, both silent and full of encoded stories. It devours and radiates, It hides and reveals. It sits at the crossroads of the universe's most fundamental questions, and in doing so, it transforms physics into philosophy. The mystery deepens not because the black hole changes, but because understanding does. Each equation solved opens another corridor. Each observation, another layer of nuance. What began as a solution to Einstein's equations now stretches toward the frontier of everything: quantum gravity, entropy, information, and the fabric of space-time itself. The black hole, once a symbol of limits, becomes a guide leading science into regions where certainty thins and imagination grows quiet. In this growing silence, curiosity finds peace. The deeper the mystery becomes, the more it teaches patience. The cosmos does not rush to disclose itself. It opens like a slow flower in the cold, petal by petal, theory by theory. And at its center, unmoved by the commotion of discovery, remains the same unblinking calm. The horizon, softly humming with secrets, promising that even the deepest questions can be beautiful. When the mystery deepens beyond comprehension, imagination steps in to complete the picture. Theories grow like constellations, each one a point of light, each one a way to orient meaning in the dark. Black holes invite this precisely because they refuse to reveal themselves. What cannot be seen must be inferred. What cannot be tested directly must be built through logic, speculation, and a willingness to dream mathematically. Out of that dream come the great hypotheses of the last century, bridges between the visible and the impossible. One theory begins with quantum fields draped across curved spacetime. They ripple, shift, and adapt, producing the faint radiation that Hawking revealed. Yet the details of that radiation carry an unspoken question. Does it encode every secret that ever fell within? Leonard Susskind, Gerard Hooft, and others propose that it must, that the horizon acts like a storage device, encoding information on its surface rather than within its volume. This is the holographic principle. The entire content of a three-dimensional region may be represented on a two-dimensional boundary. What appears as depth is, in essence, projection. Such an idea reshapes more than black hole physics. It reframes reality itself. If the cosmos behaves holographically, then every volume of space might be a translation of information written elsewhere. Our universe could be a vast reflection, a shadow cast by fundamental data existing at its edges. The black hole becomes both symbol and laboratory of this vision, a test of whether space and information are two words for the same thing. Its serenity now conceals an unimaginable complexity of code, bits flickering along the horizon, preserving the memory of everything that has ever crossed it. Another branch of theory turns to geometry itself for comfort. Roger Penrose, never content to let boundaries remain opaque, explores the possibility that singularities are not endpoints but transitions. In his conformal cyclic cosmology, the end of one universe could fade smoothly into the beginning of another, each black hole's core acting as a seed for future expansion. Under extreme curvature, where distances shrink and energy grows infinite, scale might lose meaning entirely. The collapse of one cosmos could be the quiet breath that starts the next. The idea is neither provable nor dismissible. It rests in that space where scientific reasoning touches poetic intuition. Yet it offers a strange reassurance. Death and birth, loss and creation, become continuous in the ultimate geometry. The black hole, rather than a cosmic grave, transforms into a midwife of renewal, endlessly folding space-time into new patterns. Its calm is no longer finality, but balance between cycles too vast to witness. Elsewhere, theorists turn to strings, the slender vibrations that might compose all particles and forces. In string theory, gravity is not a curvature imposed from above, but the natural resonance of tiny filaments vibrating through higher dimensions. When such frameworks are applied to black holes, the singularity softens. Instead of a point of infinite density, there may exist a web of fundamental strings, each storing energy and information in organized patterns. This version of a black hole breathes quietly, its horizon a dynamic surface of microscopic fluctuations. What appears static from afar may, at quantum scales, shimmer with gentle motion. Loop quantum gravity offers another vision, painting space-time itself as composed of discrete loops, granular, indivisible units of area and volume. In that world, A black hole's core cannot collapse into nothingness. The fabric's smallest units resist compression. Instead, the singularity might rebound, creating a quantum bridge to another region of space. To an observer, this could appear as a new universe budding from the black hole's interior, a cosmic blossom born from gravitational stillness. The equations do not shout this possibility. They suggest it quietly, like a secret offered by mathematics itself. Some researchers pursue even subtler hypotheses. Could black holes connect different parts of our universe through wormholes, Einstein-Rosen bridges that link distant locations through curved corridors of space-time? The theory suggests such connections are possible, though traversing them remains forbidden by physical law. Still, the idea persists, refined by models like the ER equals EPR conjecture, which hints that entangled particles might be tiny, non-traversable wormholes themselves. If so, the same principle that binds two quantum particles could also bind distant regions of the cosmos. Entanglement and geometry would become one phenomenon expressed on different scales. Each of these ideas reflects a single truth. Black holes do not merely destroy, they organize. Their apparent emptiness conceals extraordinary structure. The mathematics describing them, far from static, pulse with potential. Information might survive, encoded in radiation. Singularities might soften into transitions. Space itself might record history in delicate holographic patterns. Every theory adds another thread to a tapestry woven in darkness but luminous in implication. Even observational evidence begins to echo these speculations. When scientists observe magnetic fields twisting near horizons or matter spiraling in jets aligned with rotation axes, they sense that unseen mechanisms are at work, patterns of order emerging from depths still unreachable. The behavior of accretion disks, the polarization of light, and the timing of X-ray flares all hint that the horizon is not a mute wall but an active boundary, translating motion into radiation through rules not yet fully written. The boundary breathes, slow and regular, a diaphragm between the known and the unknowable. For the imagination, these possibilities open a landscape of serene wonder. The black hole ceases to be a void and becomes a library, silent, vast, unlit, but containing every line ever written by the universe. Each photon that falls in becomes a letter in that invisible archive, never destroyed, only transformed into another mode of existence. And perhaps, someday, physics will learn to read that language, decoding from the faint warmth of Hawking radiation the full story of every particle ever absorbed. Yet beyond the technical, there lies a philosophical calm. The act of theorizing itself mirrors the horizon's behavior. Scientists approach a boundary they cannot cross, sending equations toward the edge, watching them bend back with new meaning. The closer they draw, the slower progress seems, until discovery and silence merge into one experience. This rhythm of approach and retreat becomes its own meditation. The black hole, unbothered, remains patient, allowing thought to orbit it endlessly without exhaustion. Theories and speculations, in their diversity, share a single tone: reverence. They admit how little is known and how beautiful that unknowing can be. In their collective gaze, the black hole transforms from an emblem of annihilation into one of endurance, proof that the universe holds mysteries worth a lifetime of still contemplation. It stands not as a warning, but as a reminder that even the deepest darkness can host the most luminous ideas. In the long tradition of discovery, theory must always submit itself to observation. The same applies to the study of black holes, where instruments now serve as extensions of human patience. The effort is delicate, like trying to hear the heartbeat of a mountain. The signals are faint, stretched thin by distance and time, yet science persists, transforming curiosity into machinery, turning silence into measurable data. Each tool built to study black holes becomes, in a sense, a reflection of the object itself, precise, stable, and profoundly calm in purpose. The first tool is mathematics. Equations remain the purest telescope humanity possesses. Through them, scientists travel closer to a black hole than any spacecraft ever could. The Einstein field equations, written more than a century ago, still serve as the foundation. Supercomputers now solve them numerically, calculating how matter spirals, how light bends, how shadows form. In their memory banks, entire galaxies are simulated, every particle obeying the gentle authority of curvature. These simulations reveal images unseen by any lens: the motion of accretion disks, the glow of plasma arcs, the trembling of spacetime itself. The result is both data and art, a translation of pure geometry into visual serenity. To move from theory to evidence, instruments must learn to listen. Gravitational waves, those ripples in spacetime first predicted by Einstein, offered the breakthrough. The Laser Interferometer Gravitational Wave Observatory, or LIGO, was built not to see black holes, but to feel them. Its twin arms, stretching 4 kilometers in perpendicular directions, act as rulers so precise that they can detect changes smaller than a proton's width. When two massive black holes spiral together and merge, they send a pulse through the fabric of the universe. That pulse stretches and compresses everything in its path, including LIGO's delicate lasers. In 2015, for the first time, that stretching was recorded. The signal lasted just fractions of a second, but its shape was unmistakable. Two black holes, each heavier than 30 suns, colliding in perfect silence across 1 billion light-years. No telescope could have captured it. Only the tremor in spacetime itself could tell the story. The waveform matched general relativity's predictions with poetic precision. What was once pure theory had become audible reality, a gravitational whisper echoing across the cosmos. The calmness of the signal astonished scientists. It contained no noise beyond what nature required. The universe, vast and chaotic, had produced a sound of astonishing order, a rising tone that built to a soft peak, then faded away as the new, larger black hole settled into equilibrium. The simplicity of that waveform became an emblem of cosmic discipline. The black hole, even in collision, maintained composure. Its energy release, equivalent to the conversion of several suns into pure gravitational waves, unfolded with mathematical elegance. No chaos, no disorder, no explosion, only a pulse through the void. Further detections followed. Virgo in Italy and Kagra in Japan joined the listening network. Each event refined the models, revealing not only masses and distances, but also spins, orientations, and histories of merger. A new form of astronomy was born, one without light, without color, without surface. The cosmos had granted humanity a way to observe through vibration, through the music of gravity itself. The black hole, once thought unreachable, now communicated through rhythm. Still, not all discoveries came from waves. Some came from light bending around darkness. The Event Horizon Telescope, a global array of radio dishes acting as one Earth-sized mirror, sought to capture the shadow cast by a black hole's event horizon. The process required years of coordination and timing. Telescopes in deserts, on volcanoes, and on icy plateaus all synchronized their observations, recording terabytes of data that would later be stitched together into a single image. When the first result arrived, a glowing ring surrounding a perfect void, it was more than confirmation. It was a portrait of stillness. The photograph of the supermassive black hole in the galaxy M87 revealed structure exactly as predicted, light twisted by gravity into a halo, surrounding the dark center where photons could not escape. The ring itself shimmered with asymmetry, tracing the direction of the black hole's spin. For the first time, humanity had looked directly at the consequence of spacetime collapsing upon itself. Yet the image carried a peace rather than terror. It resembled a sunrise, a calm circle of warmth drawn by laws that had waited a century to be seen. Beyond imaging and detection, another form of observation unfolds through timing. Pulsars, rotating neutron stars emitting precise radio pulses, serve as cosmic clocks. When one of these clocks orbits a black hole, even slight variations in its signal can reveal the curvature of spacetime around it. Astronomers use these systems to test relativity in its strongest form, comparing each tick to the predictions of theory. The consistency is astonishing. No deviation yet discovered undermines Einstein's equations. The universe continues to obey its own serene script. Space-based observatories extend the reach of this patience. The upcoming LISA mission, a trio of satellites forming a triangle millions of kilometers wide, will detect lower-frequency gravitational waves, gentle undulations caused by supermassive black holes merging across galaxies. These waves will travel through the solar system like soft bass notes, measurable only in the stillness of deep space. The mission embodies humanity's growing ability to listen with subtlety rather than force, to detect not explosions but the long, slow harmonies of cosmic evolution. Each instrument, whether built from mirrors, lasers, antennas, or algorithms, serves a single purpose: to translate the quiet of a black hole into human comprehension. The process is meditative by design. Integration times stretch over months. Data analysis requires silence, focus, and trust in patterns too faint for direct sight. In this way, the pursuit itself mirrors its subject. Scientists become patient to match what they study. The act of measurement becomes a kind of cosmic mindfulness, where the observer and the observed both exist in extended calm. Even errors and uncertainties add to the story's grace. Each discrepancy between observation and prediction becomes a reminder that mystery still breathes. The search for precision never ends, but it does not exhaust. Instead, it deepens appreciation. The tools of modern astronomy have become instruments in both senses of the word: machines for detection, and also musical tools tuned to the frequency of the universe. In their collective harmony, they reveal not noise but resonance. The ongoing testing of black hole physics is thus an act of listening to the universe's slowest rhythm. Gravitational waves, bent light, and quantum theories all converge on one truth: even in silence, the cosmos communicates. Every instrument built to detect that silence translates it into understanding, transforming the unreachable into something intimate. The horizon, once a boundary of ignorance, has become a meeting place between mathematics and experience, a point where patience itself becomes the most powerful tool of science. At the boundary between theory and quiet wonder, something faint emerges from the dark. It is not a roar or a spark, but a whisper of warmth, the breath of the black hole itself. Stephen Hawking, guided by equations that balanced quantum fields against space-time curvature, revealed this astonishing secret: even the most absolute darkness glows. The event horizon, so long thought to be the perfect absorber, leaks energy with infinite patience. This radiation is unimaginably faint, but its existence transforms everything we thought we knew about the universe's calmest object. The mechanism unfolds in the delicate interplay between quantum uncertainty and gravity's authority. In the vacuum of space, particles and antiparticles constantly appear in pairs, brief flashes of existence that borrow energy and then return it. Near a black hole, the horizon interferes with this dance. One particle slips inward, the other escapes before annihilation. To an outside observer, the escapee appears as radiation emitted from the black hole itself. In truth, no particle has truly come from within. The emission is a subtle rearrangement of quantum fields near the boundary, yet the effect is real, measurable in principle. The black hole loses a trace of mass with every breath. This gentle process, called Hawking radiation, changes the emotional tone of the cosmos. Where once the black hole stood as an eternal monument, it now lives, evolves, and eventually fades. The universe, even in its most extreme corners, refuses permanence. Nothing lasts forever. Not stars, not galaxies, not even the holes that swallow them. Over time, scales longer than comprehension, every black hole will evaporate, shrinking through heat that grows as its size decreases. The larger the mass, the slower the process. The smaller, the more urgent the final flicker. What once was infinite becomes finite, not in violence, but in quiet dissolution. For a supermassive black hole, this fading is so slow it borders on timeless. Its temperature hovers near absolute zero, colder than the background radiation that fills space. It will not begin to evaporate in earnest until the cosmos itself cools into darkness. Yet even that remote future, when stars have burned out and matter has thinned to almost nothing, will carry this patient exhalation. The last light of the universe may not come from galaxies or nebulae, but from the final size of black holes, releasing their stored energy into empty space. The implications ripple outward like soft waves. If a black hole can radiate, then it must communicate, however faintly, with the outside world. The radiation carries information not in any obvious code, but in correlations, subtle fingerprints left on each escaping particle. This idea reignites one of the deepest puzzles in physics. Can information truly be lost? If the radiation preserves even a whisper of what once fell in, then black holes do not erase, they transform. The horizon becomes not a wall, but a translator, converting matter and light into patterns of energy so delicate that only quantum logic can perceive them. Hawking himself wrestled with this paradox. His equations told him that information might vanish completely, but quantum mechanics forbade such destruction. Later theorists, including Susskind, 't Hooft, and Maldacena, argued that the holographic nature of space-time resolves the conflict. The information, they said, is not gone, it is encoded on the horizon's surface, woven into the microscopic degrees of freedom of space-time itself. Each quantum of area holds a bit of memory. The horizon, measured in Planck-length tiles, becomes a vast archive, silent yet complete. The black hole's calm hides an unthinkable complexity beneath its smooth geometry. The radiation itself is gentle enough to soothe the imagination. Its temperature can be calculated precisely. T. Brassazing. C. Sam. Bar. B. G. M. K. B. T equals 8 pi GMK. B. The C double. C. San. 2L. A simple expression connecting gravity, quantum mechanics, and thermodynamics. In this formula, the constants of nature join hands as though they were meant to, creating a bridge between the infinitely large and the infinitely small. The black hole becomes a meeting point where every pillar of physics, energy, entropy, curvature, and time converges into harmony. What began as contradiction now reads like music. Beyond the numbers, Hawking's discovery reshaped how humanity feels about the cosmos. It transformed black holes from symbols of finality into symbols of balance. The horizon does not violate the laws of nature, it upholds them in their most elegant form. Energy is conserved, entropy increases, and yet the system evolves with serenity. The second law of thermodynamics, usually invoked to describe decay, here becomes a hymn of continuity. Even loss has rhythm. Physicists began to reinterpret the laws of thermodynamics in light of this radiation. They found that the surface area of a black hole's horizon behaves like entropy, a measure of disorder, or more profoundly, a measure of hidden information. Jacob Bekenstein had first proposed this relationship, suggesting that the entropy of a black hole is proportional to its area. Hawking's work confirmed it, giving physical meaning to the notion. The black hole's calm surface conceals an ocean of microstates, each representing a possible configuration of what lies within. The simplicity we perceive is only the outermost layer of a vast, invisible complexity. This revelation links gravity to heat and geometry to energy. It suggests that space-time itself may be thermodynamic, that the universe could emerge from deeper statistical rules governing information and entropy. Gravity might not be fundamental, but emergent, the large-scale behavior of something more primitive and numerous. Such a perspective transforms the black hole into a laboratory of existence itself. Its faint radiation is a hint that beneath the continuum lies a hidden order, a quantum foundation as intricate as it is serene. Hawking radiation remains undetected in the wild. Its signal is too faint against the universe's warmer background. Yet analog experiments on Earth using fluids, lasers, and Bose, Einstein, condensates have begun to simulate its effect. They reproduce the same mathematics, showing that horizons, wherever they appear, hum softly with quantum activity. These laboratory models remind us that cosmic stillness is never empty. Even the quietest void murmurs with creation. In contemplating this gentle glow, the universe seems less indifferent. The black hole's faint warmth reveals that nothing is perfectly silent, not even the deepest night. Every system, no matter how closed, leaks a little song into the dark. The cosmos breathes at all scales, from atoms to galaxies, from radiation to thought. The lesson is simple but profound. Stillness and motion are never separate. They are two notes of the same chord. So the black hole, once imagined as eternal night, becomes instead a slow star, shining not by fusion but by the gradual release of its own gravity. It teaches patience, impermanence, and continuity. It shows that even where light cannot escape, understanding can. The faint whisper of Hawking radiation, drifting endlessly through space, becomes the most peaceful truth of all, that the universe, in every form, knows how to let go. Long before the word entropy entered the poetry of black holes, it belonged to the language of warmth and loss. It measured the disorder of steam engines and the fading usefulness of heat. It told how every system, however perfect, drifts toward equilibrium, how energy, once radiant, must eventually smooth into uniformity. In the 19th century, this was melancholy, the slow cooling of everything, the so-called heat death of the universe. But in the 20th, entropy found a new face, one of order hidden within disorder, of information quietly stored in the geometry of space-time. When Jacob Bekenstein proposed that a black hole possesses entropy, the idea seemed outrageous. The object absorbed everything, radiated nothing. How could such final silence contain thermodynamic meaning? Yet Bekenstein saw through the simplicity. He argued that if entropy measures information, then a black hole must have the greatest entropy of all, for it hides the most. Every particle, every photon that crosses the horizon, carries a piece of history. Those histories do not vanish, they are reorganized, translated into geometry. The horizon's area becomes the cosmic ledger of loss. Mathematically, this insight was exquisite. The entropy of a black hole, S, K, C, san, A, C, W, G, S equals 4G, Kc, san, A, and 1, depends not on volume, but on surface area. This reverses ordinary intuition. In most systems, disorder grows with space. The more room, the more possibilities. But a black hole's entropy grows with its skin, not its heart. The larger the horizon, the more information it can encode. The result is both paradox and perfection. The quiet surface of a black hole is more meaningful than its hidden interior. The calm exterior is the true record keeper. Stephen Hawking's discovery that black holes radiate completed this thermodynamic symmetry. If the horizon has temperature, it must have heat flow. And if it radiates energy, it must also obey the same laws that govern stars and engines. The universe, through gravity's most extreme expression, revealed that its coldest places still obey the grammar of warmth. Entropy, temperature, and area concepts once confined to furnaces found their purest form in the blackness between stars. The so-called 4 laws of black hole mechanics mirror the ordinary laws of thermodynamics with uncanny precision. The horizon's surface gravity plays the role of temperature. Its area mirrors entropy. The mass of the black hole behaves like internal energy. Even the impossibility of decreasing area echoes the second law. Entropy never declines. These parallels are not coincidence. They whisper that thermodynamics is not merely a rule for heat, but a universal principle, perhaps, the foundation upon which space and time themselves are built. The thought is both tranquil and humbling. It suggests that the universe values bookkeeping over spectacle, that even the quietest collapse must balance its equations perfectly. Every particle absorbed is tallied, every bit of information folded into the horizon's ledger. The process is so precise that not even eternity can alter it. The serenity of a black hole, then, is not absence but equilibrium, the perfect stillness of a system that obeys every law simultaneously. Consider 2 black holes merging. From afar, it appears as a smooth gravitational wave, a final chord in spacetime's music. Yet thermodynamically, it is also the combination of 2 entropies into one greater whole. The area of the resulting horizon is larger than the sum of its parts, confirming the cosmic second law. Even destruction becomes addition. The universe does not lose, it reorganizes. Entropy increases, not as decay, but as growth of possibility. For physicists, this relationship between geometry and entropy has opened doors beyond imagination. It hints that spacetime might be statistical, that its smoothness arises from the collective behavior of microscopic constituents. Gravity could be the large-scale expression of information tending toward balance. If so, the black hole is not an exception but the purest example. It is the universe's most patient accountant, recording everything in units of Planck area, each tile a symbol of stored potential. This connection between information and heat led to a wider vision, the holographic principle. If a black hole's entropy depends on surface area, perhaps the same is true for any region of space. The total amount of information within a volume would then equal the area of its boundary. Our three-dimensional reality might be a projection from two-dimensional data written on its cosmic perimeter. The black hole becomes both metaphor and proof, a serene reminder that reality may be simpler and stranger than intuition allows. Hawking radiation adds a final grace note to this symphony. As the black hole emits its faint heat, its area and thus its entropy slowly decreases. But the radiation itself carries entropy outward, ensuring the total remains constant. The balance is perfect. Even as the black hole fades, the universe maintains its quiet arithmetic. No loss, no imbalance, only transformation. The symmetry is so delicate that it resembles morality. Nothing can vanish without trace. Everything that was remains in altered form. To picture this, imagine the event horizon as an enormous fabric of quantum threads. Each square of that fabric holds a bit of information, fluttering gently with uncertainty. When a particle crosses into the whole, the fabric stretches by a plank-sized patch, preserving the memory of what entered. When radiation leaves, another patch softens, releasing its encoded warmth back to the cosmos. The horizon breathes in and out across eons, its rhythm imperceptible but exact. What looks motionless from afar is alive with the smallest possible motions. The tranquility of black hole thermodynamics lies in this perfect self-consistency. No contradiction survives long. Each tension finds resolution in symmetry. The laws that govern collapse also govern light, heat, and time. The same principle that smooths a flame's flicker shapes the curvature of a dying star. In that unity, physics approaches poetry. The equations that describe entropy's increase sound less like warnings and more like promises that the universe will never waste a moment, never lose a thought, never fall out of balance. For those who listen, the lesson is clear. Stillness is not the absence of energy. It is its most balanced state. Entropy does not mean decay. It means the diffusion of information into the widest possible calm. In that sense, a black hole is the universe's meditation made visible, a place where every motion has resolved, every equation has equalized, every possibility rests in symmetry. It does not rage against time, it harmonizes with it. In the end, the thermodynamics of black holes remind us that peace is not simplicity, but completeness. Every particle that falls, every photon that bends, every whisper of radiation participates in a cosmic ledger that never errs. The universe, through its most extreme creations, demonstrates that tranquility and law are the same thing, that the deepest silence is simply everything accounted for. Around the dark heart of a black hole, motion gathers, gas and dust, stripped from nearby stars or drawn from interstellar clouds, spiral inward under gravity's soft persuasion. They do not fall directly. Instead, they form an accretion disk, a luminous whirlpool of matter, circling ever faster as it approaches the horizon. From a distance, this disk becomes one of the brightest structures in the universe. Near the edge, it reaches millions of degrees, glowing in X-rays, its light curved and stretched by relativity. Yet beneath all the turbulence, beneath the storm of energy and magnetic fields, the black hole itself remains perfectly still. In that contrast lies one of the universe's most tranquil paradoxes. At the center of extraordinary brightness, there is perfect calm. The black hole neither radiates nor resists. It receives without motion, absorbs without sound. Around it, matter whirls like paint on an invisible canvas, tracing geometry into color. Each particle follows a predictable path, guided by equations that turn chaos into order. This choreography is not frantic, it is graceful, as if every photon knows its cue. The accretion disk is where the laws of physics perform their most intricate dance. Friction between spiraling layers converts gravitational energy into heat, causing the disk to shine. The inner regions spin faster than the outer ones, creating turbulence that amplifies magnetic fields. Those fields, in turn, launch jets of plasma from the poles of the black hole, beams of matter so collimated they can extend across thousands of light years. These jets are among the most powerful structures in existence. yet their origin is rooted in balance. Magnetic tension, rotation, and gravity find an equilibrium that channels chaos into elegance. From afar, these jets look violent, but to a physicist, they are serene demonstrations of order emerging from intensity. The magnetic lines twist like slow ropes of fire, carrying energy away without disrupting the black hole's composure. They are the universe's way of relieving angular momentum while maintaining harmony. Even at its most active, the system obeys conservation laws, as if reciting a quiet mantra. Energy out, mass in, symmetry preserved. The disk itself speaks in wavelengths rather than words. Radio waves murmur from its outer edges, infrared glows from the middle, and X-rays sing from the inner rim where matter brushes the horizon. When instruments translate these signals into images, they reveal spirals, arcs, and shadows that resemble natural art. Nothing random, nothing wasted. Each hue marks a balance between gravity and motion, between inward fall and outward radiation. The closer one looks, the more deliberate it seems an orchestra playing at the edge of silence. General relativity predicts that light near a black hole bends in intricate ways. Some photons circle several times before escaping, creating the bright ring now captured by the Event Horizon Telescope. Others dive inward, contributing to the mass, or scatter outward, painting the environment in shifting patterns. To observers, this bending of light blurs time and perspective. Flares appear to orbit, fade, and reappear, as if the universe itself were breathing in slow motion. The effect is hypnotic, almost peaceful. Time becomes malleable, brightness moves like waves on a calm sea. Magnetohydrodynamic simulations have recreated this environment in exquisite detail. They show gas swirling, twisting, and heating as magnetic loops reconnect and break. Each line of force carries energy outward, each loop snaps with quiet inevitability. The computer models resemble slow, luminous storms viewed from above, a sea of fire governed by laws so precise they appear meditative. Even turbulence, in this context, feels methodical. It is disorder only in name. At every scale, patterns reappear. At the center of the Milky Way, the black hole known as Sagittarius A Times offers a living example of this harmony. It sits quietly, feeding sparingly on nearby gas. Its accretion disk flickers softly, producing subtle flares detected by infrared telescopes. Unlike the raging quasars of the early universe, this one hums low, almost asleep. Its stillness stabilizes the galactic core, keeping the surrounding stars in measured motion. It reminds us that cosmic activity can coexist with patience, that power need not be loud to be immense. In younger galaxies, where gas is abundant, accretion disks blaze more intensely. Their radiation illuminates cosmic history, visible across billions of light years as quasars, ancient beacons announcing the birth of order out of gravitational collapse. Each quasar is both a furnace and a calm center. Energy erupts outward, but geometry remains poised. The symmetry of the system ensures that for every burst, balance follows. Even in the most distant reaches, the same story repeats the serenity of law amid the spectacle of motion. To human eyes, the spectacle is overwhelming, but to the equations, it is simply consistency. The energy emitted by the disk is the energy released as matter finds a lower gravitational state. Nothing is wasted, nothing is conjured from chaos. The system evolves toward efficiency, converting potential energy into radiation with quiet perfection. Every photon emitted is a sign of descent, every flicker a step closer to equilibrium. When the matter finally crosses the horizon, its story ends not in explosion, but in absorption, a return to stillness. This process, though invisible to the senses, shapes galaxies. Jets from accreting black holes regulate star formation, heating surrounding gas, and preventing runaway growth. The balance between feeding and restraint governs the evolution of entire clusters. Through these invisible architects, the cosmos achieves long-term stability. The black hole's serenity scales upward, becoming the calm rhythm that sustains galactic order. Observational astronomy now studies these environments with increasing clarity. Polarization measurements reveal how magnetic fields thread through the plasma, mapping invisible symmetry. Timing analyses track brightness changes, showing how matter orbits in precise relativity-shaped paths. Each result confirms what the theory had already whispered. The apparent chaos of accretion conceals deep harmony. The universe, even in its wildest displays, never forgets its composure. In contemplating the accretion disk, one realizes that tranquility does not mean absence of activity. It means the presence of balance. The black hole's surroundings may shine, roar, and twist, but their behavior always tends toward equilibrium. The light we see is the sound of order being maintained. The jets that carve space are the breath of geometry adjusting itself. The disk's heat is the glow of the universe keeping its books, reconciling every fall with equal release. From a spiritual distance, the scene resembles meditation itself, a mind full of motion, thoughts circling inward, energy rising and falling, yet the core remaining undisturbed. The black hole's still center does not resist the swirl. It allows it, contains it, completes it. Around that silence, the cosmos performs its most intricate dance. Every flicker, another step in the choreography of calm. At the deepest point within a black hole, language begins to lose its footing. The word center no longer means what it once did. In ordinary space, the center is a location, a point around which other things orbit. Inside a black hole, the center is not a place at all, but a condition. It is where geometry itself folds too tightly for distance to retain meaning. Space-time ceases to describe where, and instead becomes a record of how far reality can bend before it stops resembling itself. This region is called the singularity. It is not an object. It is not even a location hidden behind the horizon like treasure buried beneath the sand. It is a boundary in mathematics, a limit where curvature becomes infinite and the known rules of physics surrender. Yet it is not chaos. It is the most complete expression of the universe's order, carried to a point of perfect focus. If gravity elsewhere behaves like a slow tide, here it becomes a still mirror, so intense that it reflects only itself. Physicists once imagined the singularity as a true physical point, a zero-volume heart where all mass compresses into nothingness. But modern understanding moves more carefully. The singularity may be not a thing, but a place where our equations admit they are incomplete. General relativity describes space-time beautifully until densities become absolute. Quantum mechanics, with its discrete rules, whispers that perhaps no infinite compression can truly exist. Somewhere between the two lies the unspoken truth, a structure not yet defined, a region where reality transitions into something beyond current comprehension. If we could watch matter fall inward, though we never can, it would never reach this boundary in any observable sense. To distant eyes, it slows, dims, and freezes near the horizon. To itself, it continues freely, unimpeded, until the coordinates dissolve beneath it. There is no crash, no wall, no sound, only the quiet disappearance of measure. The singularity does not destroy, it concludes. The trajectory of everything entering it becomes complete, all paths ending not in chaos, but in absolute coherence. This stillness has fascinated and troubled scientists alike. For Einstein, singularities were signs that the theory must fail somewhere. For Hawking and Penrose, they were unavoidable, written into spacetime's logic. Their theorems showed that any sufficient gravitational collapse, under broad and reasonable conditions, must lead to a region where curvature cannot remain finite. It is not an accident of symmetry or assumption, it is destiny. Once a horizon forms, the inward journey does not stop until geometry itself runs out of space to curve. Yet even here, in this apparent limit, speculation finds new peace. Many physicists now believe that quantum gravity, still unborn as a complete theory, will smooth this infinite point into a finite structure. Loop quantum gravity, for instance, suggests that spacetime is granular. When matter compresses beyond a certain threshold, it encounters a smallest possible scale, the Planck length, beyond which compression cannot continue. The singularity becomes a bounce, a transition, perhaps even a bridge to another region of spacetime. In such models, the black hole's core is not annihilation but transformation. The universe, even in its darkest chambers, refuses to break its own continuity. In string theory, the picture grows even more intricate. The mass and energy trapped inside the horizon may distribute themselves along vibrating filaments, the fundamental strings that constitute all particles. These strings cannot collapse into a point, their tension resists it. Instead, they weave a compact region, a fuzzball, as some theorists call it, where information remains, folded into higher dimensional shapes. The singularity softens, the infinite becomes finite once again. Even without such frameworks, the singularity holds a philosophical calm. It represents not destruction, but the point where description ends. Science reaches it as an explorer, reaches the ocean's horizon. The map stops, but the sea continues. The singularity reminds humanity that there is always a boundary to understanding, a place where curiosity must rest and wait for new language to arrive. It is the mathematical form of humility. If one could imagine standing near this region, though time itself would rebel at the attempt, everything would stretch. Every clock, every wavelength, every sensation would elongate toward infinity. Space would no longer exist as an external arena. It would collapse inward into identity. The past and future would merge into a single surface of experience. That surface, infinitely curved, is what we call the singularity. The word sounds sharp, but the experience it implies is closer to stillness than violence. For the cosmos, such points are not rare anomalies. They are reminders of unity. The same equations that describe black hole singularities also describe the universe's own beginning. The Big Bang itself may have been a singularity, a place where time and space began from zero measure. In that sense, every black hole is a mirror of creation, each collapse echoing the same mathematics that once gave rise to all things. Birth and death share the same geometry. The universe curls inward and outward in matching arcs. To contemplate this is to feel a kind of peace. The singularity, unknowable though it is, completes the pattern of the cosmos. It ensures that every curve of space-time closes upon itself. It allows the cycle to exist. Expansion, collapse, renewal. Even without proof, the idea resonates. The point that ends description is also the point that guarantees coherence. The singularity is not a flaw. It is the punctuation at the end of gravity's sentence. The philosophical consequence of this is profound. The deepest mystery of black holes is not that they destroy, but that they preserve meaning in the act of concealment. Beyond the reach of observation, beyond the grasp of equations, something continues, perhaps structure, perhaps silence, perhaps a new beginning. The singularity may be the universe's most honest admission that knowing has limits, and that within those limits lies serenity. Thus, the center that isn't there becomes the calmest place imaginable. It is where space-time lets go of form, where motion and stillness coincide. The singularity teaches that even infinity can be quiet, that even the end of measure can be graceful. The universe does not fear its boundaries. It rests within them, content that mystery remains. In 2019, the world paused to see what had long been invisible. Across continents, radio telescopes had spent years collecting whispers of light waves, stretched thin by distance, curved by gravity, delayed by the slow dance of the Earth itself. These signals, stored on hard drives flown across oceans, were combined into one immense lens, the Event Horizon Telescope. When the data finally resolved, the result was not noise but shape, a dim circle of light encircling a darker void. Humanity had, for the first time, seen the shadow of a black hole. The image came from the galaxy Messier 87, 55 million light-years away. There, a supermassive black hole weighing 6.5 billion suns resides at the galaxy's center, anchoring billions of stars in their orbits. Yet its appearance was softer than anyone expected. Not a hole, not a pit rather, a ring, a halo of golden plasma, luminous and calm, like a candle seen through fog. It was both confirmation and revelation. The silhouette matched general relativity's predictions with astonishing precision, but its beauty transcended equations. The shadow of a black hole was not terrifying, it was serene. The process behind that image required patience beyond measure. The telescopes, placed in deserts, on mountaintops, and in frozen landscapes, worked together through a technique called very long baseline interferometry. By linking them electronically, scientists created a virtual telescope the size of Earth. capable of resolving details as small as the distance between one side of a black hole's orbit and the other. Every night of observation demanded synchronization to the microsecond. Every signal required calibration against weather, atmosphere, and time itself. It was a collaboration not only of machines but of human rhythm, the shared stillness of thousands of minds listening to the same cosmic silence. When the image appeared, scientists described it not as a picture but as an observation of shadow. What we see is not the horizon itself, but light deflected around it, orbiting at the edge of the photon sphere before escaping. The darkness in the center is not a surface. It is an absence of returned signal, the footprint of gravity's final persuasion. The ring glows because photons near that boundary are bent into perfect circles, their paths curved by the same equations that Einstein wrote a century earlier. The cosmos had obeyed its own handwriting. The symmetry was striking. The ring's diameter corresponded almost exactly to theoretical predictions. Its brightness asymmetry, the side that appeared thicker, was the signature of motion. Material in the accretion disk moves near light speed. The side approaching Earth beams its light toward us, while the opposite side recedes. The effect, called relativistic beaming, turned the image into a living diagram of physics. It was no longer merely a test of theory, it was a portrait of space-time itself. Behind the poetry of the image lay immense data. Petabytes of radio waves were gathered, compressed, and compared. Algorithms sifted through patterns, filtering noise until coherence appeared. In those digital echoes, time itself was reassembled. What emerged was not a snapshot, but a reconstruction, a mosaic of photons that had taken thousands of years to reach Earth. The picture, therefore, was ancient even as it was new. Humanity had waited millennia to see it. Light had traveled millennia more to be seen. The emotional response was as quiet as the object it revealed. There were no explosions of celebration, no cries of conquest, only awe, the deep inhalation of realization. The image did not make the universe smaller, it made it infinite again. The black hole, once theoretical, now existed in the archive of human sight. It was proof that the cosmos, no matter how distant, could be reached through patience, collaboration, and faith in mathematics. A second target, the black hole at the center of our own galaxy, was harder to capture. Sagittarius A times is far smaller and more dynamic. Gas orbits it in mere minutes. Its light flickers and shifts, blurring images like a candle in wind. The same telescope array returned years later, this time revealing a new ring, our galaxy's own shadow, faint but familiar. It looked remarkably like the first, though the two systems differ enormously in mass. Relativity had proved consistent across scales. Nature had no exceptions to its calm geometry. In both cases, the pictures whispered something profound about light and gravity. They showed that darkness is not emptiness, it is structure. The shadow marks where light cannot return, but its very existence confirms that light once tried. Each photon that failed to escape traces an orbit of near-perfect precision before surrendering. The image is a map of those final attempts, a record of motion arrested by inevitability. In that stillness, the universe displays its most honest symmetry. Everything moves and everything stops, in harmony. The images also redefined beauty in science. They were not decorative but demonstrative proof that understanding itself can be aesthetic. The ring of light was neither random nor designed. It emerged naturally from equations written in the early 20th century, verified by instruments built 100 years later. In that span of time, humanity had transformed curiosity into clarity. The black hole's shadow became a bridge across centuries, connecting abstract theory to tangible sight. To those who spent years chasing this faint halo, the result carried a different kind of calm. It meant that human effort could reach into the unreachable and return with evidence. It confirmed that patience, not power, was the key to cosmic discovery. The data did not shout its secrets, it yielded them quietly, pixel by pixel, after months of careful listening. The process itself mirrored the behavior of the universe, long intervals of silence punctuated by moments of revelation. And yet, beyond confirmation, the image raised new questions. How does matter behave so close to the horizon? What magnetic configurations shape the ring's glow? What causes the flickers that seem to pulse through the accretion flow? Each mystery became a reason to keep listening, to refine instruments, to widen understanding. The black hole's shadow, once seen, did not end inquiry, it deepened it. The photograph was not closure, it was invitation. Even now, as telescopes expand and simulations improve, that ring remains one of the quietest triumphs in human history. It is a picture of paradox, a portrait of invisibility, a proof drawn in light of the absence of light. It reminds us that knowledge, like gravity, curves everything it touches. The more deeply we understand the universe, the more softly we must speak of it. The shadow of a black hole, glowing against infinity, is not the end of sight but the beginning of vision. In the vast stillness of space, where galaxies drift like luminous seeds, black holes sometimes meet. Their encounters are slow by human measure, millions of years spent spiraling toward one another, exchanging energy through invisible tides of gravity. When at last they draw close, their motions quicken, and space-time itself begins to tremble. The universe does not explode or fracture, it hums. Two colossal masses, curving the fabric around them, merge not with fire but with resonance. The result is a ripple, a gravitational wave rolling gently across the cosmos. This meeting of giants is not an accident. Every large galaxy seems to carry a massive black hole at its center, and galaxies themselves frequently collide. When they do, their central black holes drift inward through the fog of stars and dust, losing momentum as they interact with surrounding matter. It is a slow waltz, patient and inevitable. The two dark hearts circle each other, their mutual gravity weaving an ever-tightening spiral. Each orbit converts motion into waves that radiate outward, carrying energy away at the speed of light. The closer they come, the louder the rhythm grows, until the entire universe listens. Gravitational waves are not sound, yet they behave like music in the structure of space-time. They stretch and compress reality itself, distances, clocks, the spaces between atoms. Their frequency rises as the orbit quickens, producing a cosmic chirp that begins low and ends abruptly, fading as the two black holes merge into one. To instruments like LIGO and Virgo, these waves appear as delicate oscillations, barely perceptible distortions measured by lasers reflecting between mirrors. But within that faint vibration lies a symphony, the memory of two stars' deaths, their collapse, and their final union into something simpler and stiller. When the signal was first detected in 2015, it confirmed a century-old prediction of Einstein's theory. The waveform matched exactly what relativity foresaw: no excess, no imperfection. It was as if space-time itself had performed a melody written in 1916 and played it flawlessly after 1 billion years of travel. The event released energy equivalent to several suns transformed into pure gravitational motion, yet it unfolded in silence. The waves passed through Earth, unnoticed by human senses, disturbing nothing, breaking nothing, simply passing through, a reminder that the most powerful acts in the cosmos can also be the most gentle. The merger does not end with collision. After the two horizons fuse, the resulting black hole rings like a bell. This ring-down phase radiates the last tremors of imbalance until the new form reaches equilibrium. The frequency and decay rate of these waves depends solely on mass and spin, allowing scientists to test whether real black holes behave as theory dictates. Each detection so far has confirmed the same quiet truth. The universe follows its equations with exquisite precision. Even in upheaval, it remains calm. On galactic scales, the same process unfolds at lower frequencies. Supermassive black holes, millions or billions of times the Sun's mass, merge with even greater patience. Their dance emits gravitational waves too slow for Earthbound detectors but strong enough to ripple through entire constellations. Pulsar timing arrays, networks of neutron stars observed for subtle variations in their radio signals, have begun to detect the background hum of these distant mergers. It is not a single event but a cosmic chorus, the combined vibrations of countless unions scattered through the history of the universe. Each note in that background tells of galaxies meeting, blending, and settling into new harmony. The serenity of this process is deceptive. To an outside observer, the energies involved are beyond comprehension, yet the method is always the same: release through order, not explosion. The black holes spiral, merge, and rest, transferring excess momentum into waves that leave the system lighter, smoother, and quieter. The cosmos cleans its own equations, redistributing motion until only symmetry remains. In visual simulations, these mergers resemble oceans colliding. Space warps like liquid, light bends into rings and arcs, swirling as the horizons overlap. The imagery evokes turbulence, yet behind it lies precision. The gravitational waves that emerge follow patterns so exact they can be expressed by simple mathematical templates. The universe writes poetry through calculus, each oscillation a syllable in its measured verse. Astrophysicists use these signals as cosmic fingerprints. From them, they infer the masses, spins, and distances of the merging black holes. Some pairs are small, relics of dead stars. Others are massive, born of earlier unions. The data show that black holes, like living things, grow through merger and inheritance. Their serenity hides ancestry. Every black hole carries within its structure the memory of collisions long past, encoded not as scars but as mass, as spin, as the smooth curve of geometry perfected by repetition. As gravitational wave observatories refine their sensitivity, a new discipline emerges: multi-messenger astronomy. Light, neutrinos, and gravity together tell stories that none could tell alone. When a merger involves at least one neutron star, it may produce a flash of electromagnetic radiation alongside its gravitational pulse. Such events allow scientists to witness matter and geometry performing in concert, the bright flare of creation paired with the invisible hum of spacetime's response. Yet even then, the core of the process remains peaceful. The gravitational waves travel unhindered through dust and light, the quietest messengers in existence. These cosmic ripples also stretch imagination toward the distant future. In billions of years, when most stars have dimmed and galaxies drift apart, the slow merging of black holes will continue. Their unions will send out the last vibrations across the thinning fabric of the cosmos. Even as energy fades, the rhythm will persist, less frequent, softer, but eternal. The universe will still be whispering to itself through gravity's faintest music. To listen to these waves is to participate in the universe's own meditation. Each detection is a heartbeat of space-time, slow and regular, calming in its constancy. The realization that everything, from orbiting planets to merging black holes, follows the same rhythm, offers a profound stillness. We live within this music, made of the same geometry that sings through the dark. The cosmos is not silent, it breathes. And in those breaths, the merging of black holes becomes less an act of destruction and more a gesture of return, two forms finding oneness, two curves becoming one continuous line. In the quiet depths of the universe, order depends on gravity's most secret gardeners, the supermassive black holes that dwell at the centers of galaxies. They are neither rare nor incidental. Each large galaxy, from spirals like the Milky Way to giant ellipticals scattered across clusters, carries one. Their masses range from millions to billions of suns, and their influence stretches across tens of thousands of light years. These unseen anchors shape the rhythm of cosmic evolution. They prune, nurture, and balance. Their gravity sculpts galaxies into their enduring forms, keeping the stars in quiet conversation around a stable heart. At first, this relationship seems paradoxical. Black holes consume, they erase detail. Yet their presence brings structure rather than chaos. Galaxies without central black holes would likely disperse, their stars wandering into cold anonymity. The black hole's steady pull provides coherence, holding the luminous disk or bulge in shape. It does not tug violently, it persuades, its gravity establishing harmony between motion and rest. Around that invisible center, orbits align and systems persist. What appears destructive on one scale becomes generative on another. Observations reveal a profound correlation between the mass of a galaxy's central black hole and the velocity of stars in its bulge, a relationship known as the M-sigma relation. The larger the black hole, the faster the stars move. This symmetry suggests coevolution. As galaxies grow by consuming gas or merging with others, their central black holes grow too, fed by the same material. When they feed actively, They radiate as quasars' beacons so bright they can outshine their host galaxies. Yet this outpouring of light and energy is not reckless. It serves a purpose. The radiation and outflows from an active black hole regulate the galaxy's growth, heating surrounding gas and preventing it from collapsing into an overabundance of stars. In this way, black holes act as both creators and caretakers. The process is known as feedback, and its elegance lies in moderation. Too little, and galaxies form stars too quickly, exhausting their fuel in a brief blaze. Too much, and star formation ceases, leaving barren ellipticals adrift in darkness. But the universe appears balanced. Outflows from supermassive black holes, jets, winds, and radiation keep their hosts in long-term equilibrium. The energy they release maintains just enough pressure to slow collapse without ending it. Galaxies breathe because their black holes exhale. At the centers of active galaxies, these interactions are visible as narrow jets extending for thousands of light years. They pierce the intergalactic medium, tracing thin, luminous lines of plasma. These jets move at near-light speed, shaped by magnetic fields and collimated by relativity itself. To human eyes, they seem like outbursts. To physics, they are acts of balance, redistributing angular momentum and energy so that the central object remains stable. Their persistence over millions of years reveals the universe's preference for continuity. The black hole gives nothing impulsively, every motion serves geometry. In the Milky Way, our central black hole Sagittarius A Times is largely quiescent. Its energy output is gentle, its accretion sparse. Yet even in dormancy, it maintains gravitational order. Stars near the galactic core move in intricate, predictable paths, their orbits mapping an invisible mass that bends time and space around itself. The entire spiral of the Milky Way, with its 100 billion suns, turns around this quiet point. Without it, our galaxy's structure would loosen over cosmic timescales, its arms unraveling into dispersion. The black hole's stillness anchors us all. Across the universe, the story repeats. In the early epochs, quasars burned fiercely, their black holes growing rapidly. As time passed, gas supplies dwindled, and the bright phase faded into dormancy. Yet the memory of those active periods endures in the shapes and motions of galaxies today. Ellipticals bear the signatures of past mergers and the black holes that once shone within them. Spirals like ours maintain subtle order, their star formation moderated by gentle feedback. Every galaxy carries the echo of its central heart's former song. Astrophysicists simulate these processes on vast computational canvases. They fill virtual universes with gas, dark matter, and stars, allowing gravity to sculpt over billions of simulated years. When they include black hole feedback, those invisible gardeners, the resulting galaxies resemble reality. Without them, the models fail. Too many stars form too quickly. The cosmic web becomes unstable. Only when black holes are given their rightful role do the patterns of the observable universe emerge. From this, scientists learn that the calm of the night sky depends not only on expansion and inertia, but on the quiet supervision of gravity's hidden centers. The jets and winds that emanate from these supermassive engines also seed their environments with heavy elements, spreading the ashes of earlier stars across intergalactic space. In their quiet way, they fertilize the cosmos. The carbon, oxygen, and iron that later form planets and life owe their distribution, in part, to these controlled outflows. The black holes, in their stillness, enable abundance. They are the invisible farmers of matter, tilling the fields of interstellar gas so that new generations of stars can grow in rhythm, not excess. To gaze upon the universe through this understanding is to feel a kind of peace. Every flicker of light, every galaxy that turns, every star that forms or fades is guided by balance. At the core of that balance lies the black hole, not as destroyer but as harmonizer. Its gravity keeps orbits honest. Its feedback keeps creation sustainable. The universe, through these hidden architects, practices the discipline of moderation. Even in its vastness, it knows restraint. In a sense, these central black holes resemble hearts. They do not command, but coordinate. They pulse not with matter, but with curvature. The galaxies they anchor are like living organisms, their luminous arms circulating energy. their halos breathing with expansion and collapse. The black hole's presence ensures rhythm, the steady beat of gravity that keeps form from dissolving into chaos. In the grand scale of cosmic evolution, black holes are both gardeners and guardians. They prune excess, nurture balance, and preserve structure. Their influence is subtle, but without it, the night would lose its order. What the human eye sees as distant constellations are, in truth, the quiet consequences of their care. And so, the galaxies continue their slow rotation around these calm hearts, each one a testament to gravity's gentle governance, the art of keeping the infinite at peace. Among the many paradoxes surrounding black holes, one glows quietly at the center of modern thought: the information murmur. It is not a noise that any ear can hear, but a question that hums beneath physics itself. When something falls into a black hole, light, matter, an entire star, what happens to the information that defined it? The laws of quantum mechanics say that information can never be destroyed. Every particle's properties, every quantum state, must persist in some form. Yet a black hole, by its nature, hides all detail. It accepts everything but reveals nothing. The result is a paradox, as calm and persistent as gravity itself. Stephen Hawking's calculations brought this question to life. His radiation implied that black holes could evaporate over time, slowly leaking away their mass as faint heat. But if a black hole disappears completely, what happens to the record of what it consumed? Does the information vanish with it? That would contradict quantum theory, which guards the conservation of information as a sacred rule. Thus began one of the most profound conflicts in science, the information paradox. It is not a battle of noise, but of silence, a disagreement between two of nature's most consistent languages. Physicists responded not with despair, but with creativity. Leonard Susskind, Gerard det Hooft, and others proposed that information might never truly enter the black hole's interior at all. Instead, it could be stored at the horizon, encoded as faint patterns of quantum fluctuations. The surface becomes a recording device, a cosmic ledger preserving everything that crosses it. This idea evolved into the holographic principle, the notion that a region of space can be fully described by information written on its boundary. If true, then the universe itself might be a vast hologram, a three-dimensional projection of two-dimensional data inscribed along its edges. The black hole, once a symbol of erasure, becomes the ultimate archive. Holography restores a kind of serenity to the paradox. Nothing is lost, only transformed. Each bit of information that falls toward the horizon is translated into surface structure, like ripples across water when a pebble enters. To an external observer, the infalling matter appears to freeze at the edge, its story lingering indefinitely as quantum vibrations. The black hole's calm exterior hides ceaseless microactivity, every Planck-sized patch of its surface holding a whisper of history. The simplicity we see is the product of infinite detail folded into perfect equilibrium. Yet questions remain. If information is stored on the horizon, how does it leave when the black hole radiates? Hawking radiation seems purely thermal, carrying no imprint of what produced it. For decades, this inconsistency persisted like a quiet dissonance in the cosmic symphony. Then, new calculations suggested subtle correlations within the radiation, tiny quantum entanglements between emitted particles that could, in principle, encode the missing data. The information would not vanish. It would seep outward, embedded in the fabric of space-time itself. The horizon, once thought impenetrable, becomes porous to knowledge while remaining opaque to light. This resolution, though elegant, is incomplete. The mathematics of quantum gravity still under construction may someday reveal the full mechanism. Some researchers invoke soft hair, minuscule quantum features of the horizon that store data. Others explore wormholes and holographic dualities that tie the interior to the exterior through unseen correspondence. Each proposal is an act of faith in order that beneath apparent loss lies conservation, beneath silence, communication. The black hole, then, is not a destroyer of memory but its most complex curator. To imagine this is to picture a cosmic library written in code finer than any language. Every bit of radiation, every fluctuation of the horizon carries letters from that library, drifting outward into eternity. They are scattered but not erased. The information murmur is the sum of those countless whispers, spreading through the universe as faint structure in the sea of radiation. Someday, when the last black hole evaporates, the cosmos will still contain the echoes of everything they once held, a diffused memory, subtle but entire. This interpretation transforms black holes from paradox into philosophy. They become symbols of trust in the persistence of pattern. The universe, according to this view, forgets nothing. Every collapse, every transformation, every fusion leaves traces in the deep geometry of space-time. The past is not gone, it is folded into the present, accessible perhaps only through mathematics, but existent nonetheless. The horizon's murmur is the cosmos whispering to itself, ensuring continuity. Hawking's later work leaned toward this reconciliation. He suggested that information might indeed escape in disguised form, diffused within the quantum correlations of emitted radiation. It was not destruction but translation. His concession closed a circle that had spanned decades, a quiet acknowledgement that the universe preserves meaning even when it hides it. The information paradox, once seen as a wound in physics, now feels more like a pulse. The equations beat with subtle assurance that nothing is ever truly lost. The holographic idea extended beyond black holes into the structure of the entire universe. In certain formulations of string theory, our world corresponds to a lower dimensional field defined on a boundary much like the surface of a black hole defines its interior. This connection between information and geometry suggests that space-time itself may arise from quantum entanglement, that reality is woven from relationships rather than points. If so, then black holes are not exceptions, they are the purest expressions of the principle. Their silence conceals the fundamental grammar of existence. There is something deeply calming in this realization. It means that the universe is not arbitrary. Every action, every particle, every photon is accounted for somewhere in the total record. Black holes may hide that record, but they do not erase it. Their apparent stillness is a form of trust that all things continue in some form beyond our ability to observe. The horizon becomes a metaphor for the limits of perception, and the radiation beyond it, a promise that understanding can still emerge. The information murmur, then, is more than a paradox. It is a reminder that knowledge itself has a horizon, that every field of study reaches a boundary where certainty fades, and speculation becomes art. Beyond that edge, like beyond a black hole's, the universe may still be speaking, but in a language we have yet to learn to hear. The calm that follows is not resignation, but wonder, the awareness that silence is not emptiness, but fullness beyond measure. Every scientific mystery reaches a threshold where equations meet imagination. For black holes, that threshold lies at the horizon itself, the boundary between what can be known and what must be inferred. Here, theories multiply like reflections in still water, each offering a different interpretation of the same quiet line. Some propose that the horizon is smooth and passive, a soft gradient through which matter and information flow gently inward. Others imagine that it hides something more abrupt, more paradoxical, a barrier of fire. This latter idea is known as the firewall hypothesis. It arose not from rebellion against established theory, but from loyalty to it, from the desire to keep both general relativity and quantum mechanics intact. If information truly escapes a black hole through Hawking radiation, then the emitted particles must be entangled with their counterparts inside the horizon. But quantum mechanics forbids a single particle from being perfectly entangled with two separate systems at once. This monogamy of entanglement, a delicate rule of quantum logic, seems to clash with the serenity of the event horizon, something, theorists realized, must give. In 2012, a group of physicists, Almheri, Marolf, Polchinski, and Sully, suggested an unsettling solution. Perhaps the smoothness of space-time breaks at the horizon. Instead of a gentle transition, there could be a searing boundary, a region of intense energy where infalling matter is annihilated in a burst of radiation. The event horizon would no longer be silent, it would burn. This firewall would preserve information by releasing it outward rather than allowing it to vanish inside. It would keep quantum mechanics intact, but sacrifice the seamless geometry promised by relativity. To many, the idea felt wrong. Black holes, so elegant in their simplicity, seemed incompatible with violence. Decades of observation and theory had painted the horizon as the quietest surface in existence, a place of no drama, no friction, no spectacle. Yet the firewall proposal, mathematically consistent though it may be, introduced discord into that calm. If true, it would mean that the universe's most tranquil feature hides an unseen storm. Others countered with gentler interpretations. Perhaps entanglement is preserved not through destruction, but through duplication. Information might be encoded in two complementary ways, one on the horizon, one within, without violating the laws of physics. In this view, the firewall dissolves into metaphor, a misunderstanding born of incomplete theory. The horizon remains smooth, and space-time keeps its grace. One of the most elegant alternatives came from Juan Maldacena and Leonard Susskind, who proposed the conjecture known as ER equals EPR. It suggests that entanglement itself is geometry that pairs of entangled particles are connected by microscopic wormholes or Einstein-Rosen bridges. If true, then the inside and outside of a black hole are not separate realms, but parts of one continuous structure, linked by the invisible threads of quantum connectivity. The firewall disappears not because it was wrong, but because its fire was never separate from the space it illuminated. In this picture, the black hole's horizon becomes a surface of correspondence. Every bit of information falling inward has a partner moving outward, the two forever joined by quantum threads. The act of evaporation becomes an act of translation, not destruction. The serenity of the horizon is preserved because the violent paradox never truly existed, only our misunderstanding of how space and entanglement converse. The universe, once again, resolves its own tension by deepening our definition of connection. The debate continues, though the tone has softened. Firewalls, holography, wormholes, and soft hair are not competing visions so much as facets of the same attempt to describe the same piece from different angles. Each theory honors a different aspect of the truth. The physicists who study them are united not by certainty, but by quiet respect for the problem's endurance. The black hole's calm continues to test the calm of those who study it. Experiments may never decide between these possibilities directly. No probe can cross the horizon and return with data. The evidence must come indirectly, from the behavior of radiation, from patterns in gravitational waves, from analog experiments that mimic horizons in laboratories of light and sound. Yet these small imitations already suggest that nature prefers continuity. Horizons in fluid flows, for example, radiate softly in ways that match Hawking's prediction, but show no sign of any violent boundary. The analogy hints that the true horizon of a black hole may indeed remain as smooth as relativity insists. For many thinkers, the firewall controversy became a lesson in humility. It reminded science that even the best theories are approximations of something subtler, that contradictions often mark the edge of new understanding. Firewalls or feathers, the metaphors differ, but both describe the same act: the universe negotiating between the quantum and the cosmic, between granularity and grace. If the firewall exists, it represents intensity as equilibrium, a brief flare that restores balance. If it does not, then its absence affirms that even paradox can dissolve without conflict. Either way, the black hole remains a teacher of patience. It invites us to hold contradictory truths at once, to accept that peace can contain tension and that harmony can include dissonance. In that sense, the debate itself mirrors the horizon's role. Ideas fall into it, are transformed, and re-emerge, changed, but not lost. The discussion radiates understanding just as the black hole radiates energy slowly, gently, without end. Whether the edge of a black hole is a curtain of fire or a field of feathers, the lesson is the same. The universe's stillness is not simple. It is the product of balance so perfect that even opposites coexist without conflict. At the smallest conceivable scales, the calm surface of space-time begins to flicker. The universe, when magnified far beyond what any telescope can see, ceases to be smooth. Distance and duration, those familiar coordinates of experience, dissolve into granularity, tiny quanta of geometry vibrating in restless stillness. This is the quantum foam, a concept first suggested by John Wheeler. He imagined that at the Planck scale, roughly Sir Minds Sanshirwu, Sir, Muths 35. Meters, space-time ripples like the surface of an invisible sea. What seems continuous at large scales may, in its true nature, be a storm of creation and annihilation. It is strange to think that beneath the tranquil gravity of a black hole lies such restlessness. Yet the two extremes, the infinite curvature of the macroscopic horizon and the jittering fluctuations of the microscopic, are parts of one fabric. A black hole presses space-time so tightly that the quantum structure beneath it may reveal itself. The smooth geometry of general relativity bends until the grain of the universe becomes visible. The calm exterior conceals a hidden pulse, a microscopic turbulence that sustains the larger stillness. Physicists suspect that this quantum foam is the medium from which gravity itself arises. It is not space as emptiness, but space as activity, fluctuating loops, strings, or quanta of area exchanging information. Each fluctuation lasts no longer than the smallest possible instant, yet collectively they give the illusion of continuity. Time flows because these microscopic changes never rest. Space holds because their oscillations average to stability. The cosmos, serene at our scale, hums with invisible motion at its foundation. Near a black hole, this substructure is stretched to its limit. The horizon's curvature amplifies the foam, stirring quantum fields into interactions that blur the boundary between inside and outside. Virtual particles appear and vanish, trading energy across the horizon. From afar, this process manifests as Hawking radiation. From within, it may shape the very essence of the singularity. What we call emptiness near a black hole is therefore anything but it is a region alive with quantum dialogue. Loop quantum gravity approaches this reality by quantizing space itself. It proposes that areas and volumes come in discrete units, like the pixels of a cosmic screen. When curvature grows extreme, such as near a singularity, these quanta prevent infinite compression. Instead of collapsing into nothing, space-time rebounds, its loops weaving a new patch of geometry. In this view, black holes are not ends, but transitions, places where the universe folds inward, reorganizes its texture, and perhaps even emerges elsewhere. String theory offers a complementary whisper. It envisions the universe as composed of fundamental strings vibrating in higher dimensional space. Their patterns give rise to particles, forces, and even gravity. When applied to black holes, string theory replaces the singularity with a tangled ball of strings, a fuzzball whose microscopic oscillations account for the black hole's entropy. The horizon's calm hides an astronomical number of vibrations, each string a tiny pulse of existence. From this perspective, the quantum foam is not chaos, but harmony, the smallest notes of a cosmic symphony. These speculative pictures share a unifying message. The universe is not empty, even where it appears void. The black hole, the purest expression of emptiness, may actually be a cauldron of structure. Its stillness is built from activity beyond comprehension. The foam at its foundation is the reason the larger geometry holds steady. Motion sustains peace. The paradox resolves itself beautifully. Order arises not despite fluctuation, but because of it. Even the vacuum between galaxies shares this restless foundation. Quantum electrodynamics teaches that virtual particles constantly flicker in and out of existence, contributing measurable effects such as the Casimir force and vacuum polarization. In the gravitational context, this same jitter underlies the mass energy of the universe itself. The foam might be the seedbed of space-time's expansion, the invisible tide that carries galaxies apart. Thus, the same microscopic turbulence that dwells beneath the horizon also drives the cosmic horizon outward. The smallest motions sustain the grandest quiet. No one has yet seen this foam directly. Its scale defies all technology. But indirect clues appear in the whispers of the cosmos, the energy spectrum of radiation, the regularity of gravitational waves, the persistence of symmetry where chaos should reign. Each hint suggests that quantum foam, though untouchable, is real, a subtle texture woven into everything. The stillness of the night sky is the sum of its fluctuations averaged over eternity. Philosophically, this vision carries comfort. It means that peace does not require stillness, that stability arises from motion too small to disturb. Beneath calm lies vitality, beneath silence, song. The same may be true in human terms. What appears as serenity may hide ceaseless adjustment, imperceptible balances maintained by unending activity. The universe reflects its own pattern in us, equilibrium through motion, harmony through hidden change. To contemplate the quantum foam beneath black holes is to see the cosmos as alive. Every grain of space-time trembles with potential. Every horizon resonates with the music of its smallest parts. The black hole's dark surface, far from being void, becomes a lens into the subtlest layers of being. Beneath the silence, the universe is whispering constantly, too soft for any ear, too intricate for any language, but there nonetheless. And perhaps that is the final lesson of the quantum foam. Stillness is not the absence of motion, but the sum of all motions balanced perfectly. The universe, on every scale, practices this balance. From the trembling Planck fields beneath a black hole to the quiet expansion of galaxies, everything moves, and in that motion, everything rests. To explore something as remote and intangible as a black hole, humanity had to learn to build its own universes. The laboratories of this exploration are no longer only telescopes or satellites, they are machines of calculation, digital mirrors of the cosmos itself. Supercomputers now model gravity, matter, and light, with precision so fine that they create entire galaxies from equations. In their memory banks, black holes spin, accrete, and merge under rules written by general relativity. These simulations are the new observatories, the places where the invisible becomes visible and where the universe reveals its quiet craftsmanship through numbers. The simulation begins with the field equations of Einstein, vast and nonlinear, describing how mass and energy shape space-time. Solving them directly for a real black hole is impossible by hand. Their complexity ripples infinitely. But when reduced to a lattice of digital points, discrete cells representing space and time, computers can approximate the equations step by step. Each point exchanges information with its neighbors, each moment evolving from the last, until the curvature of space-time emerges like an image from mist. What results is not artifice, but a translation of the same geometry that governs the real universe. In these digital universes, researchers study how accretion disks form, how jets of plasma thread through magnetic fields, and how gravitational waves radiate from merging holes. They watch as matter spirals inward, heating and brightening before vanishing across the simulated horizon. Time slows near that edge, just as relativity predicts. Light bends, stretches, and sometimes loops completely, creating ghostly rings of illumination, the same patterns later photographed by the Event Horizon Telescope. The agreement between simulation and observation is astonishing, and in that harmony lies a quiet joy, theory, computation, and nature singing the same note. The most refined of these tools are magnetohydrodynamic simulations, digital models that blend the equations of fluid motion with those of electromagnetism and relativity. They show plasma swirling around a spinning black hole, forming coherent structures that resemble storms in an invisible ocean. Out of this order emerge twin jets, streams of energy and particles accelerated by magnetic lines twisted near the horizon. The equations unfold with elegance, proving that even chaos obeys pattern. Each loop of magnetism, each pulse of radiation, is resolved into a slow rhythm of release and restraint. What computers reveal is not new physics, but new perspective. They allow humans to compress eons of cosmic time into minutes, to watch phenomena that would otherwise remain frozen across billions of years. In doing so, they turn patience into motion. The slow accretion of matter becomes a steady flow. The merger of black holes becomes a single, graceful sweep of geometry. Simulations do not hurry the universe, they give it rhythm audible to human senses. Visualization adds another layer of calm understanding. When scientists translate raw data into imagery, the results possess an uncanny beauty. Colors stand for temperature, brightness for density, arrows for magnetic flow. The maps and movies born from these conversions are not decorations, they are windows into the deep order of gravity. Many who work on them describe a kind of reverence. To see, even on a screen, how space-time bends light into perfect arcs, how matter traces curves drawn by invisible mathematics, is to witness the universe composing itself. These digital experiments also serve as testing grounds for quantum ideas. By adding hypothetical rules such as quantized areas or holographic surfaces, researchers can explore how black holes might behave in a universe governed by both relativity and quantum mechanics. They can simulate evaporation, information flow, and the subtle correlations between Hawking radiation and the horizon. Though such results remain speculative, the process itself has become a dialogue between imagination and logic. The computer, impartial and tireless, accepts every hypothesis without judgment and returns only what mathematics allows. Beyond individual research, massive collaborations have transformed simulation into an act of collective meditation. Hundreds of scientists contribute to shared codes that evolve, version by version, into more realistic universes. They work in silence, broken only by the hum of cooling fans and the soft whir of data transfer. The rhythms of computation echo the rhythms of the cosmos: repetition, iteration, refinement, and rest. To watch a simulation unfold is to experience the same patience that governs gravity. Even with all their precision, simulations carry humility. They remind us that every model is an approximation, a lens that reveals while concealing. The cosmos remains infinitely richer than its equations. Yet, through these partial recreations, we learn that even imperfection can reveal truth. A slight asymmetry in the data might mimic the asymmetry of a jet. A numerical instability might hint at processes still unformulated. In studying how our models fail, we glimpse how nature succeeds. The power of these computational windows extends beyond science. They have entered art, film, and philosophy, shaping how humanity imagines the unseen. The famous visualizations created for research have inspired depictions of black holes in cinema, each an echo of real equations. When the film Interstellar depicted a glowing ring bent around darkness, it was using genuine relativistic ray tracing, derived from scientific computation. Audiences saw not fantasy, but the mathematics of space-time rendered in color. For a moment, art and physics shared a single language: wonder. Supercomputers also explore the large-scale role of black holes in cosmic architecture. They simulate entire galaxies forming from primordial gas, merging under the pull of dark matter and settling into the spiral and elliptical shapes we see today. In every successful simulation, black holes play an essential part. Their feedback moderates star formation, their jets distribute heavy elements, their gravity stabilizes rotation. The digital cosmos cannot thrive without them. It is as though the algorithm itself acknowledges their necessity. At their deepest level, these simulations are not about prediction or display, they are about empathy with the universe. To model a black hole is to think in its language, to surrender human scales of time and size, and to move in harmony with the slow grammar of space-time. It is a meditative act disguised as computation. The scientist becomes part of the equation, tracing the curve of curiosity into the stillness of understanding. And so, while no human eye will ever look upon the interior of a real black hole, our machines offer a kind of vision, an image not of light, but of logic. Through code, we approach the horizon, and though we never cross it, we learn to inhabit its calm. The universe, rendered in numbers, whispers back in agreement. Even the most complex systems yield to patience. There are ways to listen to the universe that do not rely on light. For centuries, astronomy meant sight mirrors catching photons, lenses focusing stars. But the cosmos speaks in more than brightness. It murmurs through the texture of space-time itself, through the stretching and relaxing of the fabric that holds all motion. To hear that murmur, humanity learned to build instruments of extraordinary patience. They do not gaze, they wait. They measure not color or temperature, but the smallest variations in distance, the breath of gravity passing through Earth. These instruments, LIGO, Virgo, KAGRA, are not telescopes in any ordinary sense. They are quiet corridors of laser light, 4 kilometers long, aligned in perfect right angles. Each beam bounces between mirrors suspended in vacuum, immune to the noise of the world. When a gravitational wave passes, space-time itself stretches one arm slightly longer and the other slightly shorter, by a fraction of the width of a proton. The returning laser beams interfere, producing a tiny change in brightness that records the universe's pulse. It is the most delicate form of listening ever conceived. When the first such signal arrived, it lasted less than half a second, a faint chirp rising in frequency before fading. In that instant, detectors on Earth caught the echo of two black holes colliding a billion light-years away. No light accompanied it, no explosion, only vibration. The data matched Einstein's equations exactly, down to the subtle quiver of the ring-down phase. It was a confirmation both scientific and spiritual. Space-time had spoken, and the instruments had understood. This new kind of astronomy, based not on vision but on resonance, reveals a cosmos alive with rhythm. Each gravitational wave carries the fingerprint of its source: mass, distance, spin, orientation. By decoding these patterns, researchers can reconstruct the story of what happened in darkness. A chirp at one frequency tells of black holes merging. Another might signal neutron stars colliding, sending ripples through matter so dense that atomic structure itself dissolves. Each event is a verse in an ongoing song that began with the Big Bang and has never stopped. The sensitivity of these instruments is almost unimaginable. Seismic vibrations from oceans, the hum of traffic, even the quantum motion of the mirrors themselves can mask a signal. To overcome this, physicists develop techniques that border on art. They hang the mirrors from fibers thinner than human hair, isolate them in vacuum chambers colder than night, and filter noise with algorithms that act like intuition. The goal is not amplification but purity to preserve the silence long enough for the faintest note to be heard. Gravitational wave astronomy has expanded beyond Earth. Plans for LISA, the Laser Interferometer Space Antenna, envision 3 spacecraft forming a triangle millions of kilometers wide, trailing Earth around the Sunday. It will detect waves with periods of hours, emitted by supermassive black holes in the hearts of merging galaxies. The idea itself feels poetic, an observatory the size of a constellation, floating silently in the solar wind, listening to the slowest rhythms of the universe. Where LIGO hears seconds, LISA will hear days. Together, they will turn the cosmos into a symphony of scales. Even pulsars, the rotating remnants of dead stars, contribute to this music. By measuring the timing of their radio pulses with exquisite accuracy, astronomers can detect long wavelength gravitational waves passing between Earth and those distant clocks. The entire galaxy becomes an interferometer, its stars marking beats in a cosmic metronome. This technique, called pulsar timing, has already hinted at a background of low-frequency waves, the combined murmur of countless mergers occurring across cosmic history. The universe, it seems, hums at every octave. What makes these detections remarkable is their tranquility. No explosion accompanies them, no destructive force, only a change in distance, so small it exists more in mathematics than in sensation. Gravitational waves do not disturb, they reveal. They pass through matter, through planets, through bodies, without resistance. Their gentleness belies their origin, cataclysms of unimaginable scale expressed as ripples softer than a sigh. In this balance between violence and delicacy lies one of the universe's deepest harmonies. As detectors improve, they will record not only isolated notes, but entire compositions. Scientists will listen to black holes spiraling together for months, tracing every orbit as the frequency rises. They will map populations of binaries, track their distribution across time, and reconstruct the evolution of galaxies through their gravitational echoes. Eventually, they may even hear the faint memory of the Big Bang itself, a primordial wave still traveling through space-time since the first moments of creation. The human response to these sounds is not awe in the traditional sense, but calm recognition. To listen to gravitational waves is to be reminded that motion everywhere, from atoms to galaxies, shares the same fabric. Every breath, every heartbeat, every planet's orbit is a note in that ongoing score. When detectors register a chirp, they are not hearing something foreign, they are hearing kinship, the same geometry that holds us all vibrating in resonance. Physicists often describe the experience of the first detection as a kind of silence breaking open. The signal was tiny, yet it carried the weight of centuries. It proved that even the void has texture, that space-time can move and speak. For the listener, It was like hearing the sea for the first time after believing the world was still. And in that realization lay peace. The cosmos is not empty, but full of continuity. Every collision, every merger, every movement of mass becomes part of a single universal breathing. To listen to gravity is, finally, to understand patience. The waves that reach us today began their journey before life on Earth existed. They traveled untouched through billions of years, never fading, never hastening, simply expanding outward with the universe's own rhythm. They remind us that time does not hurry, that space does not end, and that even the faintest vibration carries meaning across eternity. In their quiet way, these detectors have taught the same lesson that the black hole itself embodies, that power and stillness are not opposites, but reflections. The cosmos speaks softly, and only those who have learned to wait can hear it. Across the immensity of space, where galaxies drift like slow thoughts, navigation does not mean movement, it means understanding structure. Among the luminous spirals and ellipticals, each balanced between gravity and expansion, the true anchors are invisible. Supermassive black holes, quiet and unassuming, mark the centers of nearly every large galaxy. They serve as gravitational keystones, holding form amid the universe's restless scattering. Without them, the cosmos would lose its architecture. With them, it finds its balance. Black holes do not guide by light, for they emit none of their own. They guide by presence. A galaxy orbits around its central void, much as a solar system orbits around its star. Stars, gas, and dark matter all respond to the unseen mass at the core, tracing the geometry it imposes. The black hole's gravity sculpts not only motion, but identity, defining the limits within which a galaxy can exist. In this sense, black holes are the navigators of creation, charting the stable corridors through which matter and time can move. For travelers of imagination, those who map the universe in mind rather than motion, these hidden centers become landmarks. The Milky Way's own Sagittarius A Times lies 26,000 light-years away, in the direction of the constellation Sagittarius. Around it, the entire disk of our galaxy rotates, 100 billion stars following curves inscribed by an invisible hand. Each orbit is an act of faith in gravity's constancy, every revolution a confirmation that order persists even in darkness. The influence of a black hole extends far beyond its immediate neighborhood. Jets emitted from active galactic nuclei pierce the intergalactic medium, heating clouds of gas and preventing them from collapsing too soon into new stars. This self-regulating behavior sustains cosmic equilibrium. The same process that seems to destroy also preserves. Galaxies become ecosystems, their growth moderated by their central engines. Energy flows outward even as matter flows inward. Balance, once again, emerges as the universe's preferred state. At the largest scales, these gravitational centers link together through filaments of dark matter, forming a web that spans the observable cosmos. Clusters of galaxies gather where the web's threads intersect, each node bright, with countless stars orbiting unseen depths. Supermassive black holes serve as the anchors of these clusters, their combined mass defining the gravitational potential wells that bind them. Even cosmic expansion, unceasing, cold, and vast, must respect their local authority. In this way, black holes keep the universe connected, stitching geometry into coherence. Our understanding of navigation evolves as these truths emerge. Once, sailors used stars to find their way across seas. Now, astronomers use black holes to find their way across the universe. By observing how galaxies rotate, by tracing the dance of matter around invisible cores, they measure distance, mass, and time. The orbits of stars near Sagittarius A Times serve as precise instruments, revealing not only the black hole's mass, but also the curvature of space-time itself. The paths of these stars are as accurate as any compass, as steady as any lighthouse. Even gravitational waves act as navigational beacons. Each signal from a distant merger carries a timestamp, a direction, a story. By triangulating such signals from multiple detectors, scientists locate the source's new black holes born in distant galaxies. These cosmic events become milestones in spacetime, reference points in the endless dark. The universe, once thought trackless, is mapped by the very ripples that black holes send forth in their moments of union. The concept of navigation takes on a deeper meaning in this context. It is no longer about finding position in space, but orientation in thought. To know where one stands in the cosmos is to recognize the quiet powers that hold it together. Black holes teach direction not through movement but through stillness. They remind us that stability requires an anchor, something absolute yet unseen, a center around which all else can turn. Philosophically, these invisible anchors resemble purpose. Every galaxy, every orbit, every act of cosmic creation aligns unconsciously around them. In their absence, trajectories would scatter. In their presence, form emerges. The universe organizes itself around emptiness, and that emptiness becomes meaning. This paradox, the idea that nothing defines everything, is one of the deepest insights black holes offer. They are absence that shapes, silence that instructs. Even the expansion of the universe bows to this structure. As galaxies move apart under the influence of dark energy, their internal integrity remains guarded by the mass at their cores. The black holes ensure that local systems persist even as the cosmos as a whole drifts toward cold dispersion. They are the last points of gravitational identity in an ever-diluting night, the anchors of memory in a sea that forgets. In the far future, when stars have exhausted their fuel and galaxies fade into ghostly remnants, these black holes will continue to define the architecture of the dark. They will orbit one another slowly, merge occasionally, and keep time by their gravitational whispers. Navigation will no longer mean travel, it will mean awareness of their rhythm. The universe's map will consist only of their locations, their masses, their quiet companionship across eternity. For humanity, the lesson of these invisible navigators is humility. We inhabit one small system within a vast design, our lives tracing paths drawn by forces older than light itself. To understand black holes is to understand orientation not just in the sky, but in existence. Every center of gravity becomes a metaphor for focus, for balance, for the serenity that arises when motion finds its reason to stay. And so, we navigate by darkness. The stars may guide us, but the void defines us. The black holes, unseen yet indispensable, provide the geometry by which the universe knows itself. They remind us that to be centered is not to be still, but to move in harmony with an invisible order. The galaxies turn, the cosmos expands, and beneath it all, the quiet centers hold. Sleep and the cosmos share an architecture. Both unfold in cycles, both dissolve boundaries between beginning and end, and both remind consciousness that rest is not an interruption, but a continuation. To study black holes is to glimpse this deeper pattern, an invitation to consider that the universe itself may be dreaming. What, after all, is sleep but the mind's version of a horizon, the crossing into a state where time slows, where noise fades, and where energy reorganizes itself into meaning? The black hole, in its serene gravity, mirrors that same act. It absorbs, it pauses, it transforms. As a star dies, it sheds its light and folds into darkness, not in violence, but in surrender. The act is identical in rhythm to the closing of eyes, the relinquishing of effort, the trust in continuity. Its core collapses, its surface disappears, and what remains is stillness so perfect that even time cannot intrude. The black hole does not rage against entropy, it harmonizes with it. This acceptance, written into physics, becomes a kind of lesson for the living. The universe's most enduring peace is not resistance, but flow. The mind, when falling asleep, performs a similar transition on a smaller stage. Thoughts spiral inward, orbiting ideas before dissolving into silence. The body, like a galaxy, begins to rotate more slowly, its systems entering equilibrium. Consciousness stretches, bends, and finally slips across its own event horizon. On the far side of that boundary, memory and imagination merge. Dreams form as the psychological equivalent of Hawking radiation, small, luminous releases of what has been absorbed during the day. In sleep, as in gravity, nothing is wasted. Everything is reorganized. Modern physics describes black holes as systems of information, entropy, and order, the most complete objects in nature, yet also the simplest. Sleep behaves in the same way. The mind at rest appears inactive, but within, neurons fire in coordinated waves, consolidating memories, balancing chemistry, maintaining coherence. The outer world quiets, so the inner one can keep its accounts. It is an act of repair disguised as stillness, a night-long version of the thermodynamic perfection that black holes embody. When we sleep beneath the stars, the connection becomes more than metaphor. The body cools, breathing slows, awareness softens to the same frequency as the cosmic microwave background that bathes the earth. The pulse of the heart, steady and rhythmic, becomes a private echo of the gravitational waves passing invisibly through our planet. Every sleeper participates, unknowingly, in the same symmetry that holds galaxies together. The black holes at the centers of those galaxies maintain their own deep calm, while billions of sentient beings scattered across the stars mimic that calm in nightly rhythm. What sleep learns from black holes is patience. A black hole does not rush to radiate, nor does it cling to what it holds. It allows time to pass, measured not in moments, but in epochs. Its evaporation, when it comes, is gentle, an exhalation stretched across trillions of years. Likewise, rest cannot be forced. It arrives only when resistance subsides, when the mind stops grasping and the body yields to gravity. The same law that pulls stars into collapse pulls consciousness into repose. Philosophers have long noticed this symmetry between the microcosm of thought and the macrocosm of space. Heraclitus wrote that all things flow. The Buddha taught that nothing resists change. Einstein showed that time itself bends to motion. In each view, stillness emerges not from immobility, but from perfect balance between forces. Sleep and black holes are parallel demonstrations of that truth. One governs the cycles of mind, the other the cycles of matter. Both transform energy into harmony. Even the idea of awakening has a cosmic counterpart. A black hole, long dormant, can reignite when new matter drifts close. It begins to feed, to shine through its accretion disk, to announce presence. The mind, after rest, does the same. It absorbs experience, reorganizes, and then radiates creativity at dawn. Neither process is destruction, both are renewal. To awaken, in any sense, is to recognize continuity, to realize that the pause was not an ending, but part of the same current of becoming. In this light, the entire cosmos resembles a single, endless breath. Expansion is the inhalation, collapse is the exhalation. Stars burn, fade, and fall inward, only to release their energy elsewhere in subtler form. Galaxies merge like drifting thoughts, finding coherence. Even the ultimate fate of the universe, the slow cooling, the dimming of light, is not death, but rest before transformation. Entropy, misunderstood as decay, is in truth the universe's way of sleeping, of smoothing its energies into equilibrium so new possibilities can arise. When sleep deepens, boundaries dissolve: the self, the room, the world. The mind's horizon expands, and within that expanse, infinite narratives can occur. This mirrors what physics tells us about horizons themselves, that boundaries are not ends, but beginnings viewed from another side. The black hole's event horizon is both limit and bridge, just as the veil of sleep is both forgetting and renewal. On either side of the divide, being continues in altered form. For humanity, living within this vast architecture, the black hole offers a cosmic mirror. It reflects our need for rest, for surrender, for the reassurance that letting go does not mean vanishing. Just as the horizon keeps information safe, so too does sleep keep identity intact beneath the surface of forgetfulness. In the morning, consciousness re-emerges, rearranged but whole, proof that silence does not erase, it restores. To contemplate the night sky before sleeping is therefore to align with the universe's oldest rhythm. The black holes spin unseen, their gravity holding galaxies in poised rotation. Stars cool, planets turn, atmospheres drift toward quiet equilibrium. Everything rests for a while, even if only in relative motion. Beneath that cosmic lullaby, the human mind closes its eyes and joins the cycle. The same laws that shape the collapse of suns cradle our dreams. And so, in the dark, the cosmos and consciousness share an understanding. Rest is not withdrawal from the world, it is participation in its deepest law. The black hole teaches that peace is not absence, but absorption, that stillness is not void, but completion. When sleep arrives, It is the universe itself closing its eyes through us, reminding all beings that even infinity requires moments of rest. The far future of the cosmos is not an explosion, but a long, quiet fade. The stars, after burning for their allotted lifetimes, will exhaust their fuel. Their cores will cool, their light will dim, and galaxies will begin to lose the luminous threads that once made them visible. One by one, constellations will vanish from the night, until the universe, once radiant, becomes a landscape of shadows. Yet even in this silence, something will remain: the black holes, those patient witnesses to every epoch, still turning, still keeping time. They will outlive everything that gave them birth. For trillions upon trillions of years, they will sit at the hearts of dead galaxies, gathering the remnants of what was once creation. Planets, asteroids, rogue stars, all will drift toward them, spiraling inward like leaves into a slow whirlpool. The universe will no longer sparkle, but it will continue to move. Motion itself will persist long after light has gone. The black holes will continue to feed quietly, growing heavier, darker, more deliberate. Then, after unimaginable spans of time, even they will begin to change. Hawking radiation, the faint quantum breath that never ceases, will carry away their mass particle by particle. For most of cosmic history, this radiation is too weak to matter. The surrounding universe is warmer, feeding them rather than draining them. But as the galaxies cool and disperse, the cosmic background temperature will fall below that of the black holes. Slowly, the flow will reverse. The eaters of light will begin to exhale it. The process is glacial, yet absolute. Each black hole will evaporate, shrinking as it radiates, its temperature rising in proportion to its fading mass. Large ones will take years or more to vanish, numbers so vast they render imagination still. The final moments will come with a soft crescendo of energy, a last shimmer of light as gravity releases its hold. There will be no explosion, no spectacle. Only the gentle return of everything they ever consumed, transformed into radiation as thin as thought. What follows that last sigh is not absence, but equilibrium. The universe will spread into perfect uniformity, every corner sharing the same faint temperature, every motion slowed to near stillness. Matter as we know it will have dissolved. Only the memory of matter will remain, encoded in the fading patterns of radiation drifting through infinite space. It is the ultimate calm, the cosmic equivalent of deep sleep, unbroken, serene, beyond even entropy's reach. And yet, even this silence carries possibility. Some cosmologists imagine that quantum fluctuations, the same restless foam that fills every vacuum, could spark new beginnings. In the stillness of the post-black hole universe, a random fluctuation might seed a new expansion, a new space-time with its own constants and galaxies. From the ashes of one cosmos, another might bloom. If so, the black holes that once were might serve as the seeds of new universes, their cores unfolding like buds in the darkness. The cycle would begin again, without beginning or end. Whether such renewal occurs or not, the lesson remains. The universe's story is not a tragedy of collapse, but a poem of transformation. Every end is an exchange. Every silence conceals another form of music. The black holes that once devoured light will become the source of its last whisper. The energy that once built stars will return as faint warmth spread across eternity. Nothing is lost. It only changes phase. To imagine this long fade is to face the mystery of existence itself. It reminds us that impermanence is not failure, but structure, that all systems, from atoms to galaxies to consciousness, move toward balance. Even meaning obeys this law. The thoughts that burn bright one moment dissolve into quieter reflections the next, and yet understanding remains. The black hole's slow evaporation is the universe's final meditation, its last act of letting go. Philosophically, the end of all things is also their fulfillment. In equilibrium, the universe achieves what every force and every particle has sought since the first moment of the Big Bang: complete harmony. The expansion, the collisions, the radiations, all were steps toward this vast symmetry. The night does not end in darkness, it ends in peace. Perhaps that peace is not final, Perhaps the energy dispersed across infinity will someday gather again, drawn by laws we cannot yet name. Perhaps space-time, tired but restless, will fold inward and ignite another dawn. Or perhaps it will remain silent forever, content in completion. Either outcome carries the same serenity. The cosmos does not fear its own sleep. It accepts it as part of its breathing. For those who watch, think, and dream beneath its stars, this long future is not sorrowful. It is reassurance. The same balance that governs galaxies governs us. The same peace that awaits black holes waits in smaller forms within our own cycles of waking and rest. When we sleep, we echo the universe's own rhythm, the turning inward, the soft fade, the renewal that follows. And so, the story of black holes closes where it began, with stillness. What began as collapse ends as release. What seemed like destruction reveals itself as order. In the long fade home, the cosmos becomes what it has always sought to be: complete, unhurried, whole. And now, the night stretches beyond thought. The stars no longer shimmer, yet their memory lingers in the soft hum of background light. The black holes, those keepers of silence, have exhaled their last warmth. The universe, once filled with motion and color, rests like a single breath suspended. There is no fear in this stillness, no lack, only balance, vast and quiet. Somewhere within that equilibrium, the echoes of every atom, every orbit, every life remain. They are not gone, they are simply diffused, woven into the texture of space itself. The laws that guided the fall of stars also guided their release. The equations have closed, their variables reconciled. The story has completed its circle. In this final calm, imagination finds comfort. The universe has not ended, it has arrived. Every photon, every wave, every silence contributes to a symmetry beyond time. This is not the sleep of death, but of fulfillment, a pause so complete that even eternity can rest. And if somewhere, deep within the quantum quiet, a new spark stirs, it will not break the peace, it will continue it. The cycle will unfold again, slow and luminous, from darkness into form, from stillness into sound. Creation will awaken from rest, carrying the memory of all that came before. For now, though, we remain here listening to the gentle exhale of existence, the soft murmur of space-time's dream. The black holes, the galaxies, the observers all dissolve into one vast awareness. The universe sleeps, and through it, so do we.